Good morning, everybody. Welcome to the Vernadsky State Geological Museum of Russian Academy of Sciences. As Leah Nikolaevna told us, many of the participants went to Geologische Institute. And sometimes we know there is a mess because the institute and the museum are both named after Vernadsky. And very often I see Vernadsky State Geological Museum and a picture of Geology. So let us start, and I would like to give a first word to the president of our museum, academician Yuri Nikolaevich Malyshev.
Дорогие участники, цвет нашей геологии, я имею в виду будущее. Сегодня вы еще только получаете как бы аванс. Вот если вы обратите внимание, я прежде всего рад приветствовать вас в Государственном геологическом музее имени Вернадского. Наверное, не ошибусь, что многие из вас сюда первый раз пришли. Кто тут был много раз? Руку поднимите. Ну, это уже ветераны, а молодежь где? Так вот, я хочу вам сказать, обратите внимание налево. Вот посмотрите на эту доску, вот на эти доски, которые вас окружают. Вы видите здесь первого российского академика, Михаила Васильевича Ломоносова, который в 1745 году стал академиком Российской академии наук. И он вообще, мы считаем, его химики считают своим, но мы считаем, что он геолог, первый геолог наш. И посмотрите, какие имена идут дальше. Те имена людей, которые открывали богатейшую Россию. Я всегда говорю, чем характерна Россия? Но если многие страны мира, как бы если есть Всевышний, наверное, есть, он им определил тепло, там море теплое, фрукты, то Россия в половину себе северная страна. Но зато Бог нам ее компенсировал несметными природными богатствами, которые мы открываем с вами. Ну, я не геолог, я горный инженер, я угольщик вообще. Я шел по стопам геологов. Но я всегда знал, что впереди идут геологи. Геологи, которые открывали нам величайшие месторождения, на чем сегодня живет, в принципе, Россия. Если вы начнете, каждый день начинается с чего? Сколько стоит эта бочка, баррель? Так кто открыл эти месторождения колоссальной нефти? Геологи. Геологи, которые шли в тайгу, шли в нехоженные места на комаров. Кто открыл Норильск, алмазные трубки и так далее. Можно перечислять бесконечно. Это такой труд. И я должен сказать, что сегодня мы все проходим эволюцию. И, на мой взгляд, геологическая профессия тоже проходит большую эволюцию. Нельзя сегодня сравнивать геолога, который открывал, скажем, Норильский никель в 20-х годах и шел раздетый, разутый, с молотком и находил это все. Сегодня уже довольно серьезно геологи, профессия оснащается современными аппаратами, современными приборами. Даже наш маленький музей, посмотрите, у нас, вот вы сегодня пойдете по залам, смотрите, у нас висит беспилотник, маленький самолет. Кто бы мог подумать, но мы сегодня ведем большую тему, на этот самолет навяжутся магнитометры, которые мы туда привешиваем, и он уже будет использоваться в поисках разведки месторождений. Поэтому сегодня можно много говорить. Я хочу пожелать вам хорошей работы. А лично для каждого из вас я бы хотел, чтобы через какое-то определенное время ваши фамилии появились на вот этих досках. Пожеланием вам успешной работы и успехов в жизни. Спасибо.
I will very briefly translate what Yuri said. First of all, he asked you to pay attention to the desks on the wall. This is a list of Russian academicians in the field of geology and mining sciences. And the first name over there is Mikhail Lomonosov, world-famous Russian scientist, founder of Russian Academy of Sciences. But not everybody knows that also Lomonosov was a philosopher, he was mathematician, chemician, physician, but he himself said about himself that first of all, I am mining engineer. And the first degree Lomonosov got was in mining engineering in Myburg. Also, Yuri said that geology changes right now. There is evolution of profession. Geology became technological in comparison what was 50 years ago. And he wishes you the good work through the conference. He invites you to our expositions. And he hopes that the young people who are present here at some time will see their own names on this wall. So now it's my turn. Okay. It was quite difficult to make a proper presentation for this event. And I decided to try to briefly tell you about the institution, about the museum you are in right now. First of all, no, it doesn't work. Oh, yes. A bit of history. In 1755, Demidov's brothers, who were famous Russian entrepreneurs, and they owned mines in Urals and in the other places of Russia, they gifted a collection of minerals and rocks to the Moscow State University. It took quite a time, from 1755 to 1759, to bring this collection from Urals to Moscow. But still, 1755 we believe to be the date of foundation of our museum. The museum stayed in the Moscow State University, and at the beginning of 20th century, the university already didn't have the rooms for all the collections. And after initiative of Vernadsky and Pavlovs, academicians Pavlovs, architect Roman Ivanovich Klein built this building. It was built especially for geological museum. They started to construct it at 1914, and the end of construction was in 1918. Even October Revolution didn't intervene with the construction. Then, in 1922, the museum was transferred to the Moscow State Geological Prospecting Institute. I am not sure, but I think it was probably the only institute in the world which was targeted geological prospecting, only geological prospecting, nothing else. And you can see that from 1929 to 1989, generations of students, generations of geologists went through this building. And maybe you even can feel when you enter here, there is a kind of aura. It is very warm environment, which was fed by generations of students. In 1989, the Geological Prospecting Institute got a new building at the southwest of Moscow. And there was quite a fight around this building, but the museum won. The museum was transferred to Russian Academy of Sciences, and since 1989, we keep the name Vernadsky State Geological Museum of Russian Academy of Sciences. Very few numbers. The museum has 75 employees, among them 28 researchers, 24 PhD, including 2 academicians of Russian Academy of Sciences. The total space here is 5,491 square meters, and almost 1/3 of it goes for permanent expositions. In 2015, we had 13 research projects and published 47 scientific papers. You see, we are relatively small, but still there is not just museum, there is science. Please push the button. Володь, нажми кнопочку. Не работает. What can be wrong? Владимир, можно на следующий слайд? Жень, посмотри, в чем там дело. Следующий слайд нужен. Technology. Okay, I hope it will work. Next. So, what do we do here? First of all, of course, we are keeping studying and demonstrate our collections. We don't have exactly how many samples we have, because when the museum belonged to Geological Prospecting Institute, we had a lot of expeditions here. By the way, I was graduated right in this building. And everybody who went to the field, of course, everybody brought collections here, and not everything was registered properly. Right now, above 80,000 of 300,000 are already properly documented, and we are working on it permanently. Research projects in different fields of earth sciences. I will tell about them a bit later. The third kind of activity, educational activities. We are working with schools, universities. I also will tell about that. And different kinds of social events, conferences like this one, concerts, and others. Что, каждый раз так будет? Oh, yes, okay. Here you may see just very few of our new expositions. This is the upper left. You can see minerals of pegmatites, then imitation of travel in the space. During this travel, everybody can find out how many he would wait in different planets. And women like Mercury most of all, because the weight is quite vogue. Then amber exposition, and at the bottom, the very new exposition, we've opened it just a month ago. It is about underwater research. We have here Argus bathyscaphe and imitation of going to the mid-ocean ridge. Starting talking about the research, I can say that the first and the most advanced direction is metallurgy. This direction was led by academician Rundqvist for a long time. And I will talk very briefly only about the most important achievements in different fields of our research. The first one, I believe, is a database on large and super large mineral deposits of the world. Also, this database contains only 1,700 mineral deposits, but the idea was very simple, to start from the largest deposits and go down slowly. I would say this is maybe the most representative database for the world mineral deposits, because the deposits we have in this database, they represent about 80% of world mineral reserves. And you don't see there any small or occurrences, any small deposits. You see only the largest ones. The second achievement in the field of metallurgy is a specific prognosis software. I will talk about it a bit later. Also, we deal with 3D geological modeling. Yeah, oh, sorry. This is how our database on the world mineral deposits looks right now. As I told, there is about above 1,700 mineral deposits in the database. And talking about prognosis software, I would give you just an idea how it works. You can see on the left, let us say, some system of faults, and the dots represent known mineral deposits, reference objects. Of course, when we talk about building predictivity map, the most important is distance between different criteria, in this case faults, and mineral deposits. So on the left, we talk about known deposits, reference objects. On the right, we can see the same system of faults, but we distribute a lot of random points through all the area. And we look the on the distribution of the distances in the case of random objects and in the case of reference objects. If the criteria we have under consideration, in this case the faults, if they are not statistically connected with the mineral deposits, we will see the picture on the bottom right. This is a random distribution of the distances. But if there is interconnection, we will have a different picture. And it is very simple to define and even quantitatively to evaluate if the criteria has any meaning in terms of building prediction map or not. If we have random distribution, it means there is not statistically statistically important connections between criteria and deposits. But if we have a picture like the bottom left, it means it should work. This way, we evaluate different criteria: geophysical, stratigraphic, magmatic, and so on. And the prognosis software is able to do all these operations in automatic and semi-automatic regimes. Next, this is just what we did in 3D geological and geophysical modeling. We even had some commercial projects using Australian-made software, 3D GeoModeler, with some of our inventions. The most difficult work was a 3D model of coal deposit with over 200 layers. It was quite difficult, but we did it a couple of years ago. Another, maybe a bit unexpected field of our research activity is geothermal energy. Starting from 2007, we organized a lot of workshops in different regions where we have geothermal resources. The work actually started because of our connection with French Geological Survey, BRGM, but we found it interesting enough. And it didn't work until 2013. In 2012, at the end of 2012, beginning of 2013, we organized a couple of workshops in Grozny, Chechen Republic, and this workshop worked like an ignition for development of geothermal projects in Chechen Republic. Right now, we are proud that we, together with Grozny State University, named after academician Millionchikov, we've built the first in Russia geothermal plant, which is based on doublet technology. 2 wells, one production well and another one reinjection well. Heat exchanger, and now you can see this is a 3D model of, on the left, upper left, we have a 3D geological model. We've been very lucky to have such a place because you see it is anticline, and the layers go very close to the surface. At the depth of 100 meters, we have temperature 95 centigrades. So we built this model. We've chosen the place for our plant. You see, in 2014, we already had drilling work at the site. 2015, the plant has been built, and in 2016, we already tried cucumbers from greenhouses that are heated by geothermal energy. And the last one I would like to mention in some details. We are working now, it is already the third year, we are working on UAV-based magnetometer. It differs from attempts that are known in Canada, mainly. Some attempts have been made in States, in Russia. Usually people want just to take the magnetic sensor, to place it at the UAV, and to use the same scheme as is being used in traditional aeromagnetic survey. It means they need compensation of deviation, a lot of equipment. The UAV becomes quite heavy. In our case, we minimized, first of all, we minimized magnetic influence of the UAV on the sensor. And together with our partners from St. Petersburg, we've developed a new sensor. And you can see that through this work, through 2 years, from the regular construction of the drone, upper left, we were forced to come to the new, absolutely new plan. Right now, we went through all the ground tests. Everything works. The UAV doesn't intervene with magnetic sensors located at the ends of the wings. And in June, we are planning our first flight. We will keep a special symposium at the Geological Congress in Cape Town, together with our Spanish partners who are also working on this subject. And everybody who will be there is invited to the symposium, and also to our exhibition stand, where we will represent first results of magnetic survey with UAV. UAV itself can be carried by 2 people. It is being launched from catapult. So in fact, it can be delivered in any place very easily. Fully automatic regime. We just have to establish the scale of the survey and the margins of the area, and it brings magnetic map after its flight. Also, I will not go into details, but we have high-level professionals in paleontology, gemology, geoinformation systems, anthropogenic mineral deposits, history of geology, and geological risks. So you see, a small museum, but we are quite active, not just in museum activities, but as well in research activities. So let us go to educational activities. Everybody knows it is not just in Russia. There is a huge problem, a gap between generations. We have high-level professionals in geology who is above 60. We have youngsters who are just starting their careers in geology, in mining, who are mainly below 30, maybe 35, and we have a gap between these generations. We've decided that the museum can improve the situation, and last year we established here what we call Inter-University Academic Center of Navigation through Professions of Mining and Geological Profiles. For the most important universities in this field entered this center. We had 4 rectors sitting behind one table. It was the first time in their life. And right now we are working, this center works with school children, with students. We organize for these guys, we organize for them field trips. For students, we organize summer practice in different enterprises. And of course, we are working with companies. So we have a chain: school, university, industry. Also, in this center, we have a special communication room where we organize online lectures, workshops. By the way, right now our conference is being translated on the web. So everybody who was not able to come here but would like to hear what we talk about can watch on the web our conference. Just examples of different events with children. All these events have taken place in our museum. And you can see, we see here 10 years old guys, we see here students, PhD students. So we hope that what we do will facilitate this connection between different generations. And the last kind of our activity, as I told you, social activities. Last year we have over 60 concerts here in the museum. We have here the only Fazioli piano in Russia. It was brought to us by Raspatskaya mine. And you will see today the beautiful, what we call white hall, where we have most of our concerts. Sometimes we have concerts over here as well. So I told you about our collections. I told you about, it doesn't like animation, I think. Yes, about our research projects, educational activities, and our social events. One more time, welcome to the Vernadsky State Geological Museum. I hope you will have some time to visit our exhibitions. And please, everybody, feel here as at home. You can join us in our social activities. We are always happy to have here scientific events, social events. Everybody is welcome. Thank you. I feel like this is a theater of one actor, one mic, another mic. Okay, so now I would like to invite Ernst Richard from Canada with his presentation on large igneous provinces, links to supercontinent breakup, climate change, including extinction events and major ore deposits.
All right, thank you. It's an honor to be here, and I first of all thank the organizers for the invitation to participate and for our hosts in this building and also at the Vernadsky Institute. Let me take you on a tour of an aspect of earth sciences that I think is growing in importance, and it's the area of large igneous provinces. Okay. I first am going to provide an overview of large igneous provinces, and then look at some of the frontier areas, which include the areas in the title. Supercontinent reconstruction, link with environmental effects, link with various classes of ore deposits. And then I also want to do and show some of the very impressive large igneous provinces that we now recognize in Russia. Okay. So with respect to large igneous provinces, we are talking about very, very large magmatic events. Let's see, if I know some people over here can't see. Can I adjust it all? Can I move this a bit? Yeah. Yeah. Okay. So we're talking about three aspects. Very, very large volumes of mainly mafic and to some degree ultramafic magmatism. We're talking about typically a very short duration of emplacement, and we're talking about events that are mainly an intraplate setting. In terms of scale, for some of these events, they are at least 100,000, oh no, let's see. Oh, I don't mean to. Can we go back? Okay, the pointer doesn't seem to work so well. Okay, it's hard to see. Okay, so 100,000 cubic kilometers, which in terms of the scale of Russia would represent an event that would cover the entirety of Russia to 5 meters. There are events, oceanic plateau events, a type of large igneous province, that cumulatively could be 80 million cubic kilometers, which would cover the entirety of Russia to 4.5 kilometers. We are talking about events that are placed in a very short duration. Some of them are less than 1 million years for such volumes and an intraplate setting. So they are not associated directly then with plate tectonic boundary processes, not spreading ridges, not subductions, but intraplate, and we think of them mainly linked to mantle plumes. Here's a beautiful example of some of the flood basalts of the Siberian trap event. When we talk about continental flood basalt type of lips, those are what I think in the Russian literature is usually talked about as traps. And here is a beautiful example. Another aspect of this is the plumbing system. When you erode the volcanic portion away, you're left with the feeder system. And the feeder system consists of huge swarms of diabase dikes and sills and layered intrusions. This is from northern Canada. It represents our very large, giant radiating dike swarm. Can't really see the pointer there, but in the left diagram, you see a swarm that extends out about 2,000 kilometers, radiates away from a mantle plume center on the far northwestern portion of Canada. You see in the image there dikes that are about 100 meters wide going across the countryside. Individual dikes like this could extend down, individual dikes here, we think, could extend all the way out for 2,000 kilometers. And a point about these dike swarms is that we think the magma is generated in the mantle plume center area and injected laterally out through the swarm, sideways in the crust for these distances, so that the magma originates from a mantle source area underneath the mantle plume center here and moves sideways through the crust. It's a dramatic idea, but we have lots of evidence for that. I won't have time to discuss that today, though, I don't think. In terms of the lip family, large igneous province family, we consider the flood basalt component, as in this one from the Columbia River, or the preceding image from the Siberian Trap event, and the associated volcanic rifted margins, because these are associated with rifting and formation of new oceans. The plumbing system component, consisting of dike swarms, sill provinces, and layered intrusions such as the Bushveld. A class of associated intrusive types, carbonatites and some kimberlites are associated with large igneous provinces, and also some silicic provinces, both intrusive and extrusive. In the Archean, there are examples that we think represent large igneous provinces in the Archean. Typically, those are ones which contain komatiitic magmas, evidence for high temperature magmas. Much of this is typically continental. In the oceanic areas, we have ocean basin flood basalts, oceanic plateaus that represent mantle plumes coming up, producing large igneous province in an oceanic setting. This shows the distribution of large igneous provinces for the last 500 million years. A similar record continues all the way back to 2,500 million years ago. This shows the areal extent of volcanics and also the intrusive component. Here's the Siberian Trap event. Here's Antang Java, a major oceanic plateau that, together with Manihiki Plateau and Hikarangi, cumulatively in volume represent nearly 80 million cubic kilometers of material in place in a very short time. This represents a number of other events, and I won't go through all the details there, but you can see that these events cover large areas and therefore represent, as we will see, significant sources of volumes of magma, but also fluids and heat that contribute to ore deposit formation. Okay? The record is very robust. We figure that these things come out somewhere on the planet every 20 or 30 million years. This global barcode you can see well populated with red lines marking events back through time. You see a particularly dense abundance in the youngest record where the oceanic plateaus are well preserved. However, given closure of ocean or disappearance of ocean basins prior to 200 million or so, that prior oceanic lip record is gone. It is preserved in deformed orogenic belts and will probably eventually be recognized and sorted out. But at this point, we suspect that the density of overall lips that we see here, which is something like 1 every 20 million years or so, is actually the true density back through time if you consider the observed continental flood basalts and the predicted number of associated oceanic plateaus. The links are important, and we'll go through some of those. Links with extinction events, very robust. Links with regional domal uplift of a scale of about 2,000 kilometers across and a kilometer or so up in association with an underlying mantle plume. Link with rifting and breakup. We think that every major breakup margin through time, continental breakup margin, is associated with a large igneous province. Link with ore deposits, and there are also some implications for oil and gas and in the aquifers. And there are also planetary analogs, and we also recognize on Mars and Venus, etc. And we also see some Archean analogs, as I mentioned. I'm not going to go through everything, but I want to go through some thematic aspects that I think are particularly interesting and dramatic and important as we go forward. The first represents timing. There's been an enormous amount of new results in recent years showing the incredible shortness, the brevity of some of these events, where massive volumes of magma are placed in unbelievably short geological periods. First of all, with respect to the Deccan event, you see these very nice uranium-lead diagrams, and you see the results and there's a theme here that I'll reiterate also, is that these events tie in very tightly with known extinction events. So with respect to the Cretaceous tertiary boundary and the demise of the dinosaurs, the precise date shows that the main phase of eruptions initiated about 250,000 years prior to the extinction event, and that over 1 million cubic kilometers erupted in less than 1 million years, so in about 750,000 years. So that demonstrates that the Deccan event of India, the flood basalt event of India, was associated with the end Cretaceous extinction event. Of course, it's also known that the Yucatan Peninsula meteorite impact was at about the same time. So in this particular case, it's a 1-2 punch. A meteorite impact and the flood basalt or lip event caused the end Cretaceous, the end of the dinosaurs. As we go back in time, okay, one of the other dramatic events at 200 million years ago is the Central Atlantic Magmatic Province known as CAMP. It's associated, it's found on North America, Africa, and South America in this reconstruction, and represents the event that just precedes the opening of the Atlantic Ocean at 200 million years. And you see there's also a radiating dike swarm on all blocks here, and a well-defined mantle plume center here at the center of activity. In terms of age, this shows the known extinction, the end Triassic, beginning Jurassic extinction boundary, and you see that these very precise dates from Blackburn et al., and this is right straddling the extinction event and continuing a little bit younger, but notice the scale here. This is 500,000 years here. So this is incredibly tightly linked with the end Triassic extinction. Finally, dramatic results with respect to Russia's most dramatic large igneous province, the Siberian Trap event at 250 million years. I have a diagram later, of course, to show the event, but you can see that the boundary is the extinction boundary, the Permo-Triassic extinction boundary is well defined here, and you see precise uranium-lead zircon ages just preceding, associated with, and continuing afterward. But again, look at the scale here. This is just from here to here is 1 million years. This is really the smoking gun that the Permo-Triassic extinction was caused by the Siberian Trap large igneous province. However, not all large igneous provinces are such incredibly short duration. There are others that seem to be multi-pulsed and extend for some 10, 20, or 30 million years. As an example, this is the Keweenawen Rift event of North America between Canada and the U.S. And it represents a lip event that started to break up the continent here, and so it is multi-pulsed in the sense that there's an initial mantle plume event and a second pulse associated with the onset of rifting. It didn't succeed in opening up North America because at the same time on this side there was compression associated with an orogenic event, an ocean closure event. And so despite the attempt at opening a new ocean, it was prevented by prevailing plate boundary stresses. A little bit more about the link with extinction events. I showed the examples with respect to the Deccan event, the Central Atlantic Magmatic Province at the end of the Triassic, and the Permo-Triassic events as good here, here, and here with the large igneous provinces associated. As well, many of the other times of major extinctions are associated, many of these peaks then are associated with known large igneous provinces. Of all of these events, the one that doesn't yet have a lip event is the End-Ordovician event. However, I think we're on the track of that with respect to some units that at 440 or so that we see in the Verkhoyansk region and some of the units that I know Andrei Izok is working on down in Mongolia, I think, that are representative of around 440 million years. So I think we're on track with the potential to also include this one. But nevertheless, it seems that the extinction record through Earth's history is primarily linked to large igneous provinces. There's an aspect that I don't think I'm going to have a chance to discuss, which is to say that the full range of processes that link a large igneous province to extinctions is complicated and multivariate. It turns out that you can have large igneous provinces that cause global warming by pumping lots of CO2 into the atmosphere. Turns out you can also have large igneous provinces contribute to global cooling and ice house conditions, as the Sturtian glaciation seems now linked to a large igneous province, where part of the story is that weathering of basalts is a huge drawdown for CO2. And so if you have your large igneous province mainly in a tropical area, the weathering will draw down CO2 dramatically and could put you into a glacial time. So this is with respect to the Siberian Trap event. You see a range of ways that it contributes to terrestrial mass extinctions and marine mass extinctions. And I won't go into all of details, but it's a complex story, but it is part of the way then that we see large igneous provinces contributing to extinction events, but also in a broader way contributing to dramatic changes in atmospheric conditions and seawater composition as preserved in the seawater in sedimentary record. I want to now go to another topic here, which is with respect to continental reconstructions and the role of large igneous provinces with respect to that. One of the sort of holy grails of earth science is to sort out the reconstruction of continental blocks through time. We understand the supercontinent Pangaea very well, and we have strong reasons to expect that there were prior supercontinents at about 1 billion, known as Rodinia, at about 1.7 billion years ago, known as Nuna or Columbia, and then in the late Archean, whether it was a single supercontinent or multiple large continental masses is not clear. And what's not clear is the exact configurations at any of these Precambrian supercontinent reconstructions. There are some robust attempts at reconstructions and some aspects of the Rodinia reconstruction as a result of a major IGCP project a few years ago, and some aspects of the Nuna-Columbia reconstruction and some aspects of the late Archean reconstructions are in fact well known, but in the main, these reconstructions have lots of uncertainties, and the individual placement of any particular block should be taken as speculative in most cases. There's a new IGC project, 648, which is a global supercontinent reconstruction and global dynamics one that is, I think, over the next few years going to yield some serious progress. And part of that progress is going to come from the more ardent use, more systematic use of the large igneous province story. If you look at the Pangaea story, the Pangaea breakup, and the Gondwana portion here, is really dramatically linked to large igneous provinces, as I said. First of all, the Central Atlantic Magmatic Province here is linked to the breakoff and the opening of the Central Atlantic here, breakoff of North America. Each of these other stars represents mantle plume centers and associated large igneous provinces associated with the breakup of pieces of Gondwana. So the Parana-Etndeka large igneous province here at 130 million years is associated with the opening of the South Atlantic and the separation of South America and Africa. The Karoo event at 180 in southern Africa and adjacent portion of Antarctica associated with opening here. There's the Madagascar lip at 90 million years ago, the Deccan lip at 65 or so. And so each of these is associated with the opening of and breakup of Gondwana. So we expect that the exact same pattern works back through time. And so one of our goals in understanding large igneous provinces through time and finding the mantle plume centers is to try and use that technique to figure out the reconstructions back through time. This is the Superior Craton of Canada, Archean age crustal block. We now know that this block has been cut by major events, lip events through time, each of which has an associated radiating dike swarm here, each of which has a mantle plume center at the edge of this crustal block. These two here, the Mistassini event and the Metachuan event here, are specifically conjugate to what we think is the Cola Corellia crustal blocks at the time with the same age of magmatism. And from this side, we recognize that there are two discrete plume centers here that are associated with this range of magmatism. We also have other centers here, 2100, 2080, and we think there's other crustal blocks here. On this side here, we're also experimenting with the idea that Zimbabwe was attached at this time in the Paleoproterozoic and maybe the Yilgarn Craton of Australia, and so on. So we suspect that as we push this methodology back in time, find more and more radiating dike swarms, we'll have a fuller picture of how the blocks are to be reconstructed. So how do we do that? One of the things, the approaches that we use is what we call lip barcoding. If we've got several crustal blocks here, and we have known lip events, remembering that they are in many cases very short duration, if we've got a certain pattern on one block and another block, we can look for correlations. Here we see that Craton A has many matches with Craton D here. And so this is high likelihood that Cratons A and D were near neighbors. On the other hand, Craton A and B have no matches. There's no matches here. Craton A and B were not nearest neighbors. The other thing is we can use restoring radiating dike swarms. Here, an example that I was showing before, we have radiating dike swarms that we continue into Cola Corellia, maybe Zimbabwe and Wyoming. And so that technique of the radiating dike swarms is useful for reconstructions. One of the key things then is being able to date dolerites. We've gotten very good at it these days. The mineral bedelliite is particularly useful in that it is not inherited and does not survive metamorphism. So if you get a bedelliite age from a dolerite, it is the emplacement age. It is not inherited age. So we're very good at dating dolerites now, and using bedelliite, and paleomag and geochemistry are very important as a correlation tool to extend, the paleomagnetism then obviously is a good tool for reconstructions once you have the age for a unit. We had a major industry-supported project over the last few years where we had $1.5 million from industry for systematically going around the world and dating dolerites. And we did a lot of that work in Siberia in particular. And as I'll show you, we were able to produce some new ages that recognized a whole bunch of major large igneous provinces, Precambrian, in Siberia that we didn't know about before. We produced about 220 uranium-lead ages, bedelliite ages. Okay. And one of the sort of prizes of that then was we produced about 9 uranium-lead ages from southern Siberia, and that led us to a reconstruction of southern Siberia. Lake Baikal would be here with northern Canada. These are the Arctic islands of northern Canada. Southern Siberia, not northern Siberia. This is Alaska here, a piece of Alaska that presumably was in here as well. And we just had this published in Nature Geoscience. And what we found then was by looking at southern Siberia and northern Laurentia here, and all the yellow boxes here indicate new events that we dated through uranium-lead bedelliite dating. We find a whole bunch of matches throughout the time from 700 million years all the way back to 1900 that demonstrates an attachment between southern Siberia and northern Laurentia for over 1 billion years in the Proterozoic. And some of the events then that get reconstructed into this are quite exciting. Dramatically, we have this huge event in northern Canada called the Franklin Large Igneous Province. And that is, it consists of a huge radiating swarm here. It covers about 2 million square kilometers in northern Canada, extends over. It has major mafic, ultramafic magnetism in the northern part here, and we interpret this to be the mantle plume center. On the Siberian side, we have this event we've now called the Irkutsk event. Here's Lake Baikal, here's Irkutsk here, and we have a bit of portion of a radiating swarm. The intermediate section here, which presumably would have radiating dikes, is not exposed. I do hope that, I'm very intrigued about the drone technology which can, for magnetic mapping, which you mentioned at the beginning here. I'm very curious about the availability already of aeromagnetic data that will allow us to see dike swarms and the potential for such stuff as more aeromagnetic data is collected. Canada has benefited from having near total aeromagnetic coverage in the 60s and 70s and 80s, and so it's been a huge boon for us being able to trace dike swarms, but also for basic geological mapping. Anyway, we interpret that the mantle plume center for the Irkutsk event is also here, and so this provides a very tight constraint on this. There is interesting mafic, ultramafic magnetism associated. The Davurin, the Upper Kingosh, Tartai blocks are intrusions here that are of economic nickel, copper, PGE interest. So this whole event is interesting, and by combining it, we're combining the Siberian portion with the Irkutsk portion into a single event. And so the study from the Canadian side and the Russian side represents an opportunity for a more full understanding of what was originally a single event that would cover about 3 or 4 million square kilometers. Here's another event. We have the huge Mackenzie event in northern Canada that you saw in the other diagram. And we have a dike here in, a major dike in, I think it's the Sherezhagai block of southern Siberia there, that's about 10 million years younger. So it's our first sniff of the continuation of the Mackenzie event. Otherwise, I want to draw attention to this event here. Here we have a radiating swarm. Here, this is the Chara-Sinsk-Valui area here. And so you have a radiating swarm here in the Chaya area, in the Aldan and the Anabar Shield, precisely dated dikes, a radiating center here. We also have the same age in adjacent in Laurentia. We also have a major event here, 400-kilometer long dikes, precisely dated at 1870. Dike here, the same age, and then we have a major province in Slave Craton of the same age. I mentioned the talk yesterday by Ilya Prokopiev, talking about Seligdar carbonatite, which is approximately in this area and is similar age to these dikes. This is a theme that I think is going to apply throughout. As we develop the framework of the large igneous provinces, we will be able to hang onto that frame all sorts of ore deposits that are linked to these events. And this, for instance, would be an example then of these carbonatites being linkable to this slip event. Look a little bit now specifically at the area of exploration. As we look through the record, we see an association between some of the largest lip events and major types of ore deposits. Nickel laterites in the Caribbean, associated with the 90-million-year-old Columbia Caribbean lip. Of course, the magnificent Norilsk nickel-copper PGEs, associated with the Siberian trap lip. In Central Asia, there's Morantau gold, which is at the same age as the Tarim lip. It's a more complicated relationship in there that there's also major shear zones there, so it's not just, there's an age association with the lip, but there's also other controls that seem to be related to the Morantau, but there is an age link and some genetic influence, presumably from the Tarim lip. Siberian diamonds, many of them then seem to be associated with the 370-million-year-old Yakutsk-Valui lip. SEDEX deposit in Western Canada associated with this lip. Olympic Dam, this magnificent IOCG deposit in southern Australia, in the Gawler Craton, is part of this major mafic, ultramafic event. The Palabora carbonatite, which has major copper ores. is exactly the same age as the Bushveld large igneous province. Hammersley iron formations in part are associated with this Woongoora Wili Wuli lip of the southern Pilbara craton of Australia. This is another look at the lip family here, flood basalts and a range of ore deposit types associated, the plumbing systems and some ore deposit types associated silicic magmatism, associations, carbonatites and kimberlites, Archean examples, oceanic plateaus. So there's a bit of a developing framework for what kind of ore deposits one might expect. And we've distilling this into a sort of 5-part classification on how lips can be related. This is work I've been doing with Simon Jowett, where one category is lips are the primary source of the commodities. So with respect to nickel, copper, PGE associated deposits, Norilsk, this would be this kind of deposit. And we find that most of the world's major nickel, copper, PGE deposits are linked to lips. The other thing is lips also provide the energy to drive hydrothermal systems. This is an aspect we're trying to develop more. And as we'll see, it also can affect the maturity or over-maturity of hydrocarbons. Lips, particularly sills and dikes, can act as barriers to fluid flow and or as reactive zones. So as fluids are moving through, they either get blocked or they get precipitated out by the sill or the dike. And they can also, from a hydrocarbon perspective, they can also be a structural trap. And then weathering of lip rocks, laterites, and then in this category, I'm also going to mention the oceanic anoxia events that are linked and which are the source rocks for hydrocarbons. This is with respect to then several large igneous provinces here. Here's the Siberian Trap event, the on-craton portion, the portion in the West Siberian Basin, and here's Norilsk area here. Here's the Mantle Plume Center, here or here, depending on how this is defined on the base of the radiating swarm here. So this is proximal to the plume center. In the case of the Mackenzie event, the muskox intrusion, famous in classic differentiation literature, the muskox intrusion, that's part of this event, and that has some interesting mineralization that's near the plume center. Here's a major in northern Canada, the Circum-Superior Large Igneous Province at 1880, associated with the Thompson Nickel Belt mineralization and the Raglan Belt mineralization. And at least this portion is close to the plume center. Here, in this camp event, the Freetown layered intrusion, major in terms of PGEs, it's in the vicinity then of the plume center. So our story at this point, as we developed it, is that in many cases where you want to look for associated nickel-copper PGEs is proximal to the plume center. But there's also probably a link with a whole range of hydrothermal ore deposits, and this is an aspect that we're still trying to sort out. This is from a paper in Franco Perano, but other people, this has also been reproduced in a number of other publications. You can see the nickel-copper PGE of Talnak and Norilsk here, but you see all these other types, commodity types here that are distributed quite widely and there's also in a paper by Borisenko where you can see all of these different kinds of ore deposits, including mercury and gold and antimony and copper and molybdenum, widely distributed and of age similar to and slightly younger than the Siberian Trap event, and in some way, therefore, likely being influenced by it. The details of that association are not well sorted out apart from the age correlation. You also, okay. So to jump to another aspect here is with respect to kimberlites. A few years back, it was recognized that in the Bastar craton here, which is a portion of India with a deep lithospheric root, it has some kimberlites of age that are the same as the Deccan large igneous province. So in this particular case, one can envision a mantle plume that comes up where the lithosphere is thinner here. You produce flood basalt magmatism. Where the lithosphere is thicker here, that portion of the plume ends up producing kimberlites. When one looks at South Africa here, very rich in kimberlites of a variety of ages. These are color-coded then in terms of their ages. And you can see an age-wise correlation with some of the plumes in the vicinity. Here's the Madagascar lip at this time, known from magmatism on Madagascar, which was reconstructed here at this time. And you can see a whole bunch of kimberlite groups that are tied in age-wise with the Madagascar plume. There's a whole bunch of plumes that are kimberlites tied in with the Paraná Atendeka lip at 130 million, and also apparently in the Congo craton. A lot of kimberlites of the same age. So this mantle plume here, which was responsible for magmatism in South America and the Namibian portion here of, or the Atendeka portion of Africa here, and ocean opening up the breakup there, is also responsible for, seemingly for contributing to kimberlite magmatism over a wide area. And with respect to Siberia, as we were seeing the other day, that there's quite a large number of kimberlites that are associated with the, at around 360 million years ago, that are associated with the Yakutsk plume center and the Yakutsk Veluy lip here, which is shown here. This is the plume center here. You see major Charasinsk, Veluy Marka rift systems here, so a beautiful radiating rift system, beautiful pattern of radiating dike swarms with some complexity associated with the opening along this zone here, but overall a radiating pattern here of impressive swarm. And these associated kimberlites, which are out, I think are out here, are diamondiferous and associated with this lip. These kimberlites here are slightly younger than the Siberian trap event, but are close and are probably linked with the Siberian trap plume, and so on. However, some kimberlites clearly are not plume-related, and there is an argument for plume where you have sort of a hotspot track beneath continents. So while oceanic hotspots do not continue much into continental areas because they have a hard time getting through continental crust, the overriding of a plume by a continental crust doesn't necessarily, does seem to allow the potential for some of that kimberlitic magmatism to actually traverse the continental crust. And so this example from Larry Heeman and Bruce Kiersgaard shows an age progression from northern Canada here down into the Great Meteor Hotspot tract of a kimberlite tract, and then becoming a normal hotspot tract. Wow. This is another aspect that Dr. Polozov and others and the group from Oslo have been working on, dramatic stuff with respect to the role of hydrothermal vent complexes, interaction of this intrusive component, and particularly sills, with sedimentary rocks, and the release of major amounts of volatiles from that as a major component of how large igneous provinces cause extinctions. So this is an exciting area in the Siberian trap. In particular, there are hundreds of these things. The green triangle here, see, and then these circles here are all hydrothermal vent complexes, and these here are filled with magnetite. So potential, and some of these are being mined. So this is a component of large igneous provinces that we did not recognize till about 10, 15 years ago, and it seems to be a ubiquitous portion. Thank you. Okay, thank you. I think we'll be good. This is just one aspect where there's sort of an indirect link. One of the things we're thinking about is, as you go back in time, it's hard to know when continental breakup is happening. But the large igneous provinces seem to, in their association with breakup, they also provide us a way to date timing of breakup. And so if you have breakup in one side of the planet, elsewhere you're going to have convergence. So the timing of breakup should represent the timing of increased convergence or transpression elsewhere, which has some implications for ore deposits. orogenic ore deposits, then may be correlated time-wise with timing of breakup on some other part of the planet. That's part of the reason we've had gold companies interested in our work, because of the potential of making that link. Oh, yes, so just three aspects. Oceanic plateaus as a cause of anoxia events that produce black shales and represent as source rock oils. The thermal pulse from a large igneous province can cause maturation or overmaturation of regional hydrocarbons. Dolerite sills as cap rocks for, here is, for instance, an oceanic plateau, the Caribbean large igneous province, and leading to an anoxia event that could produce black shales and so on. There are a lot of anoxia events back through time here, and many of these then are linked in with oceanic plateaus, particularly the Selly here with Antang Java, and all of these at around 90 million years ago with these large igneous provinces. And just a little bit of a thermal pulse can take you from immature to mature to overmature in terms of hydrocarbon composition. For example, when you look at the camp event in Morocco here, in this particular, or in Algeria, in this particular basin, you have a thermal spike that's recognized in the record there at 200 million years. That is exactly linked with the Central Atlantic Magmatic Province event. So in summary here, we were looking at, in terms of LIPS and resource exploration, a variety of ways that there are links. Primary source of the metals, heat to drive the engine, barriers to flow, reactive zones, surface processes, and indirect links. Just a couple other things I want to talk about. One other theme, which is sort of a new area. We've been recognizing radiating dike swarms for a long time. This is the Mackenzie one. This is the Franklin one here that we saw before. This is another one here that we recognize in northern Canada. They are ubiquitous. We're finding them all over the world now and back through time. Here's the Central Atlantic Magmatic Province as well. There's a whole new class of radiating or swarms that we're just beginning to recognize. We call these giant circumferential swarms, giant circular swarms. Here at Lake Victoria in the East African Rift System is a beautiful 180-degree circumferential system. This portion here will probably be revealed whenever the war stops in the area here and we can get proper aeromag. So 600 kilometers across. This one here would have a radius of about 300 or 400 kilometers. Here, the Siberian trap event, there's a circumferential swarm here in addition to the radiating circumferential swarm. Here in the high Arctic, this is 1,700 kilometers across. So we're talking about a circular swarm, not on the scale of an individual volcano, but something that is hundreds to over 1,000 kilometers across. These events are the same kind of thing that we see on Venus. This is where planetary comparisons help. On Venus here, you see rift systems here in red, volcanoes that are up to 500 kilometers across in green, these circular structures called corona. These circular structures called corona are characterized by these circular systems here. Here's the largest one, which is 2,600 kilometers across. We think that the circumferential swarms we're seeing on Earth are the terrestrial analog of these features that we see on, we recognize on Venus. So we have a planetary program. Please. What's going on? So just in terms of, we're just at the end here now, and just to say that we have a mantle plume comes up, it partially melts, it produces some magmatic underplating at the base of the crust, it produces an array of true intrusions within the crust, including dike swarms that extend out for maybe 2,000 kilometers in a radiating pattern, and maybe circumferential swarms that also extend quite far. Then it feeds surface volcanoes. So that's the plumbing system. Some magnificent Siberian events here. The Siberian trap event here. The Yakutsk-Valui event here at 370 and associated with kimberlites. This 1750 million year old Siberian lip event, which in terms of overall extent extends over half the Siberian craton. It's certainly a major event on par with the Siberian trap event. And it's precisely dated at 1755 plus or minus a few million years. So it's going to be one of these very, very short events. Okay. With respect to, this is a Kola Karelia here. You see our two mantle plume centers here. There's all this layered intrusion of two different pulses here in Karelia and Kola, and which will probably should be linkable then either this center or this center depending on age. A major event in northern Siberia in the Anabar Shield here, that's all 1,500 million years ago, and potentially part of a reconstruction with the Congo craton and San Francisco cratons. And then all these events that we see shared between southern Siberia and northern Laurentia, which, yeah, and I think, this is the global barcode again. You see so many events linked with extinction events, linked with regional uplift, which I didn't detail, linked with rifting and breakup, linked with ore deposits, and a little bit in planetary and Archean analogs. For more information, well, I have a book that just came out a year or so ago. The book's being translated into Russian, actually. And check out this website, largeigneousprovinces.org. We have a feature called Lip of the Month every month. So Lip of the Month, we've been doing this for 10 years. It covers terrestrial examples, flood basalts, Archean examples, Proterozoic examples, examples from Mars, Venus, the Moon, and Mercury, and so on. So Lip of the Month on largeigneousprovinces.org. And that's a final beautiful shot. Thank you all. Спасибо за внимание.
Thank you, Richard. I think we have time for maybe a couple of questions, please.
What's, in your opinion, the best example of time-constrained ligaments, like reactivation of the same structures on reactivation of the same structures on the continents, time-constrained?
Yes, it's an interesting thing to think about. You know, the relationship between each separate event. It's oftentimes people say we've got one continental block, we have one event after another. But if you take the global perspective, that's happening anyway. So in an individual block, if you have something that's 50, 60, 100 million years different, those are separate events. The blocks have moved. Those are separate events. So, however, there does seem to be areas where you've had repeated activity, and part of that might be that if you think of plumes coming up randomly, if they come up underneath an area with a very thick lithospheric root, they're going to tend to come up and then slide along the root to shallower areas. So there may be, right, so they're not going to come up and do anything underneath the thick Siberian craton. They're going to slide off to the side of the Siberian craton. And so there's going to be a tendency then for these events to be channeled to areas of thinner lithosphere. So that would be some reason why you would have repeated activity in some areas.
Is the 90 MA Madagascar plume the same as 130 at Andeka and the same as 180 Karuk?
Well, I think those are entirely different plumes. And one thing about the 90 million, you have 90 million Madagascar, you have 90 million Columbia Caribbean, you have a 90 million year pulse in high Arctic large igneous province. So you have at least 3 different nodes of 90 million, almost exactly the same age, in very different parts of the planet. So even those, I'm not sure what the relationship is. It may be something happening in the core at that time that put an extra pulse into, a little quickening of the core and putting an extra pulse of thermal energy into, the core mantle boundary. But, yeah.
Lee Nikolaevna, please.
Still, there are voices against plume.
There are. Yes.
Can you name the strongest?
Yeah, Jill. Can I name the strongest?
Strongest against.
Oh, there's sure people like Jill Folger and the late Don Anderson and others who certainly argued that mantle plumes, or Warren Hamilton, or various people who've argued that mantle plumes are not the cause for these large volume, short duration events. I think as more and more data is accumulating, I think it's harder for such a position to be maintained. As one increases seismic tomography evidence, we're seeing increasing evidence for the actual conduits of mantle plumes. I think our story related to radiating dike swarms is particularly dramatic. We're finding more and more of these giant systems which radiate away, and now we're also developing these circular structures. You have point sources of this magmatism. That seems best explained by a plume. And then there's arguments related to, the impact. The impact is also hard to sustain. When we look on Venus, for instance, where we can see impacts very clearly and magmatic centers very clearly, and they are entirely different looking. So, yeah.
Please, just the last question. We are getting out of time.
First, thank you very much for very interesting presentation. So, in particular, you mentioned some relation between hydrocarbon production and the relation with some events. My question, do you think that this enormous version of hydrocarbon accumulation might be related with some major tectonic?
I'm at the learning stage, and I'm very interested in that question of various reservoirs around and what the controls are. I don't know very much about it yet, so I'm really trying to learn to see whether there are other examples where what are the specific influences for magmatism. So I don't have an informed opinion on that yet, but.
It's all completely applicable to the case of Eastern Siberia, for example. I'm fascinated with this indeed. But this enigma, how this enormous quantity of hydrocarbon produced in this respective area,
Yeah.
from Persian Gulf.
No, I would like to, I want to.
Do you think is some, the major igneous event behind these?
Well, it depends what the ages are. We now have a good timing of events now. We have a much better understanding of the timing. So we now have the tool from the magmatic side to compare with the hydrocarbon side and the understanding of, when the hydrocarbons form, when they get moved.
This is Cretaceous. Yeah, but it might migrate in the area.
Oh, really? Okay. Well, that's exciting because there certainly are Precambrian events that would be potentially relevant, right? So there's a timing of formation of the hydrocarbons, the timing and the causes of migration, so there's. You're somebody who I would like to chat more with about this because I want to explore this area more.
Thank you, Richard. Okay, I can feel that there are many questions, but let us leave it for coffee breaks. Richard, thank you one more time. Leah Nikolaevna Kagarka, academician of Russian Academy of Sciences.
I would like to try to connect alkaline magnetism also to plume activity. At least I will try. Alkaline and carbonatite magmatism characterized by extremely high or potential for strategical metals. Super large deposits of rare earth, niobium, radioactive elements related to these rocks. And last years, the interest to these rocks increased dramatically due to increased consumption, especially rare earths. The price for rare earths now may be 4 times higher than 7, 8 years ago. In Russia, there are 2 very large alkaline provinces. One is Mainichak-Atui area. I don't know if it's possible to see. And it is part of Siberian plume because our data show that the age of all alkaline rocks there, 250, so it is just the same age for Siberian track system. And another, no, yes, and another very large alkaline province is Kola Peninsula. And there are 3 super large deposits of critical metals here, which are the principal source of strategic metals in Russia. And last year, during the conference, each year we organize alkaline conference. Last year it was held in Apatity, and Professor Williams Jones called Kola province the heart and the soul of alkaline magmatism. And we were very proud of that. In the central part of Kola Peninsula, there are 2 very large complexes of peralkaline nepheline sands. Ozera massif represents lead intrusion, very big, about 4 kilometers, which we saw. We don't know the bottom of this intrusion. And that was formed during 2 main phases. There, see here, light green and dark green. You see one cut to another. You see here very nice layering. This is the central part of Lavozera rocks. The composition of these rocks very close to nepheline cyanide, classical. And the main ore mineral of the first deposit is laperite. You see the formula here. And this mineral is very interesting because it contains about total 30% of rare earth, high niobium, tantalum, titanium, that was mined during very many years and started at 30s. And our data show the distribution of rare earth in this laperite. You see the light rare earth much concentrated here compared with heavy rare earth. And in the vertical section of first intrusion, the structural forms of laperite change. In this part, in lowest part, laperite crystallized very late when rock-forming minerals already create rigid framework. At this stage, convection ceased, and in this part of intrusion, we don't have any laperite ore. But about 800 meters from the below, laperite changed the morphology of the crystals, and laperite became very early phase, crystallized in the big volume of melt together with rock-forming minerals, and appeared the first laterite ore seams. Interesting that laterite ore connects with rhythmic layering part of Lavoisier intrusion. Here you see laterite ore, and so at that stage, laterite became liquidous phase. So the primary magma was undersaturated in respect of laterite, and after the crystallization about 1/3 of magma chamber, laterite initial melt became saturated in respect of laterite, and laterite accumulated in this ore seams. The composition of laterite changed systematically in the vertical section of the intrusion with the increase of strontium, niobium, and dramatically decrease of rare earth. So the most productive of laterite ore in the low part of deposit, and the most productive for niobium, actually, and for radioactive elements in the upper part. So we believe that the laterite ores were a result of several factors. First of all, very important early catechtical saturation of primary magma in respect of ore mineral. Second, the evolution of alkaline magnetic system, crystallization from the bottom of this very large intrusion, and the mechanical and gravitational accumulation of laterite in the base of each rhythmic layer. Not enough. Yes. Как следует. So laterite associated in the lowest part of rhythmic layering, maybe the heaviest phase. Second deposit, also super large, associated with the second intrusion and situated in the upper part of Lavoisier method. The main ore mineral is eudialyte. You see here very complicated composition of eudialyte. And you see here the chemical composition. So very high zirconium, hafnium, and also quite high concentration of rare earth. And our data show that it is different spectrum of rare earth. And with a high concentration of medium and heavy rare earth, so this ore is very expensive as compared with laterite ore. But the concentration rare earth much more in laterite. Also, in vertical all intrusion, this is the upper part, this eudialyte complex. Also change in this part of intrusion. Eudialyte creates, you see that backscattered electron image, a very interstitial grains, and which crystallize also very late when convection stops. But after the crystallization, about 2/3 of all volume of Lavoisier magma chamber, eudialyte create very nice crystals, and eudialyte ore you see here. And the problem arises here. The specific gravity of eudialyte is much higher, of course, than alkaline melt. But all ore eudialyte situated in the very upper part of the intrusion. And first of all, some workers believe that eudialyte ore is result of metasomatic process. We investigated primary inclusions in eudolite ore. It's typical magmatic inclusions, homogenized about 900 centigrade. So this is a magmatic process. And we believe that, propose that eudolite in the beginning crystallized in very small crystals, formed very small crystals. It is a crystal eudolite, it is a central part. And in this intrusion, there are many dikes rocks. And in these dikes rocks, you see eudolite, that is a bright particles. And some of them extremely small, look at that, practically nanocrystals. So we believe that during the convection, these nanocrystals were stirred up to the upper part of intrusion, and eudolite emerged to the upper part, and because of that, the most productive part is the upper part of Lavoisier. And later, these small crystals recrystallized, and because of that, in eudolite ores, for instance, we found such crystals, a lot of small crystals here, and even broken crystals. So this is a mesh of small crystals later recrystallized, because the crystallization of alkaline, teralkaline rocks, extremely long period, because the solidus close to 500 centigrade. Because of that, the process of recrystallization is very typical for this deposit. So we believe that also, so very substantially, the primary magma must be saturated in respect of our mineral at the early stage. Only in this case we can have such type of deposit. There is another massive hibina. It is much bigger, and it hosts the world's large magmatic apatite deposit. This massive built-up conical and ring type of intrusion. Here, this apatite intrusion. And the scenery, quite beautiful, very large valley as a result of moving of glaciers, and the structure of apatite deposit presented here. This is a contact with lake rocks. In the upper part, there is sugar apatite ore, very fine grain apatite ore with practically no interstitial melt. In this part, this is apatite nepheline and pyroxene, mostly geolitic composition. And in the basement of this apatite intrusion, there is extremely big, thick layer of mesopyrite rocks, which consist of 90% of nepheline. And also primary inclusions showed us that this is a typical magmatic process, and homogenization to aluminosilicate melt. I stress it because still geologists believe that this is a miscibility phenomena here. Here you see the apatite ore, extremely small. I apologize. Yeah, it doesn't work. No, work. Very small crystals. It's an cumulative structure here. This is underlying urtite. You see the crystals of nepheline here, and also deposit for alumina. That's about 25% alumina here. And our data show the distribution of rare earth in apatite ore. You see here, quite rich, and because it's gigantic deposit, so it's enormous potential for rare earth. And we investigated experimentally system apatite nepheline dioxide, and the average composition of apatite intrusion, which was calculated using mapping, its local geologists calculated that plot to the field of Nephilim, but not far from catectic, eutectic here. But if it is dry system, if you add some water, this catectic will move in this direction. But there is an miscibility field here, but there is a thermal divide because this point and miscibility. So we believe that the crystallization of this apatite intrusion simultaneously crystallized nephilim, dioxide, and apatite. But the question arises, how these minerals distributed in a magma chamber. And for that aim, we used Bartlett model. It was presented very long ago, but I think very good in convection. And the distribution of mineral particles in magma chamber under the condition convection show that size of crystals squared, very big, but the difference between specific gravity of mineral and melt rise to the -2/3. So this is the most important value here. We calculated the distribution of these minerals in magma chamber, but also we noticed extremely high sorting apatite ore and underlying urtite. It also tells us that convection was very important. This is a distribution of this mineral, but you can see better here. This is a theoretical model, which is what we have in nature. So the most important mechanism which was responsible for such origin of such a big apatite deposit is crystallization, differentiation, and behavior of particles in the vertical section. So we propose that apatite form a very small crystal. And for instance, here you can estimate that this is a thin section of underlying urtite. You see nephilim, 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 and this is apatite which was trapped with the interstitial melt. So we believe that during the crystallization and convection, nephilim continuously sank, forming underlying urtite. Meanwhile, small crystals of apatite emerge to the upper part of the intrusion. The mechanism very similar to the formation of udalite deposit. The question arises, what was the source for such enriched magnetic system as polar rocks? And we did some investigation of isotopic system. We investigated samarium, neodymium, rubidium, strontium system. Here you see the results. And this data very close to Fosa reservoir, which is considered as a signature of plume connection. And also we investigated the lutetium gadnium system. This is Hibina and Lavozera, Hibina and Lavozera here. And also it flowed to the OIB field, which is also hint us that plume system was responsible for that. Our new data on lead isotope system also show that it is close to depleted mantle array field. And interesting that Lavozera ores and rocks characterized by extremely unradiogenic lead, maybe the most unradiogenic in the alkaline rocks and carbonatite. And so we believe that this unradiogenic lead in Fosa signature, so this is some kind of line of mixing line. So, and what was contaminated to create such unradiogenic signature? And we believe that definitely there is noticeable contamination by the basalt and lead intrusion with the age 2.4, 2.5. Data showed that the intrusion characterized extremely unradiogenic lead. And this is a part of early Proterozoic plume system, Matechivan, which Richard mentioned. So this is a Kola Karelia part of this super plume. I believe it was a very big plume system. So we believe that Devonian plume was contaminated by Proterozoic plume. This is just data of Smolkin, he is here, and Mitrofanov. They believe that plume was this area, but in fact, data show that it is a part of a plume system in Superior in Canada, in Wyoming and Huron. Interesting that all our data for rocks and for ores, strategical metals, plot to the depleted part of this mantle array diagram. This is a Harmer review for carbonatites. Majority, statistically, also plot to the depleted part. So this is a paradox. From one side, carbonatites and alkaline rocks represent the most enriched magmatic system in the globe. But from other case, they were generated from the depleted mantle, which lost already practically majority of strategical metals and rare metals. So I believe that to explain this fact, it is possible to attract the metasomatic input of these rare elements to the zones of magma generation, but very shortly before partial melting of this system to avoid radiogenic intergrowth of this reservoir, because we saw very depleted signature. And so I believe that short-lived enriched reservoirs in mantle were the source for such unique deposits. And we investigated these fragments of such reservoirs in mantle. So mantle xenoliths with strongly metasomatizing feature. For instance, we collected in Canarian Islands, this Montana Clara Island. You see carbonate here, OPX substituted, very big zone of reaction, and as a result of this reaction, CPX and olivine second generation appear, and apatite we found in these zones, and these zones characterize high concentration of rare earth as well. Another example, we found such nodules in Fernando de Noronha Island, and you see in bazanite, you see also orthopyroxene substituted by reaction zone. And here the traces of analysis, carbonate here, and also here the second generation CPX olivine. And also we found here barium strontium sulfate here. It's oxidized condition of this metasomatical event. And this is extremely interesting result. This is nodules from East Antarctica. And also OPX, unstable in this metasomatical event. And here a lot of mica. And we were very lucky because we found in this metasomatical zone, Henry Myelite, this mineral which was found 1 year ago before our publication in carbonatite, in Kavdor method. You see this is Henry Myelite, and look at that zonation here. I will tell you a little bit later about that. And here, just the composition of this Henry Myelite, you see that extremely high volume, 18%, and niobium and apatite, which we found here, also contain quite high concentration of rare earth. So the geochemistry of this metasomatical zone close to the geochemistry of our alkaline rocks and deposits. This is just some nodules we analyzed. You see also in some of them, light rare earth much higher than heavy rare earth. And the main reaction here, you see here, this is orthopyroxene, and the primary magma carbonatitic must be dolomitic because that is experimental data. Wiley and others, we don't have melt calcite straight from the mantle, only as a result of this reaction. I would like to stress it because many workers believe that carbonatite just possible to melt out from the mantle. I think that is not possible. No. Also, I would like to draw your attention to apatite in this metasomatical zone, also characterized by zonation. This zonation tells us that this process is extremely fast because the coefficient of diffusivity under mantle condition quite fast. But we still have that, and Henry made it also. So I believe it is proof that it is very short-lived enriched reservoirs, which was the source for this super large deposit. And I think the picture like this for students, so plume going up and metasomatical zone appear. It is some quite old metasomatical zone, and the partial melting to this metasomatical zone created this alkaline rocks and deposits. The analysis of our database on carbonatite and alkaline rocks showed that alkaline magmatism and carbonatitic appear somewhere 2.5 to 4.7 billions of years. This is a very important boundary between Archean and Proterozoic. And the appearance of alkaline rocks coincide with several global geological events. First of all, many geologists believe that at that time the geodynamical regime of our planet changed. Plate tectonic began. Some of them don't accept that, but I think majority think that this is really the beginning of active, at least, plate tectonic. And the intensity of alkaline rocks increase. The same for carbonatite. They also, but carbonatite and alkaline rocks, this is of course one association. But interesting that kimberlite also the intensity increased in geological time, but kimberlite appear later. At least in our database, we don't have very old kimberlite. But interesting that the diamondiferous of kimberlite in the evolution of decrease. So we believe that 2.5, close to this data, oxygen atmosphere appeared. Big oxidation event happened. Caused the oxidation of all sedimentary rocks in oceans, and the development of plate tectonic at that boundary stimulated the subduction already oxidized material containing a lot of CO2 and water. And as a result of that, the oxygen fugacity of mantle fluid also increased. But many scientists believe that the major process for oxidation of mantle fluid is disproportionation of iron to the core. For instance, Eric Galimov, Allegra. But I believe that also this oxidation, influx of oxidation material to the mantle also played some role for that. And according to experimental data, oxidized fluid phase in mantle very able to transport alkalis, silica, and a lot of elements, including the strategical metal elements. But redoxy fluid phase cannot do that. According to Fallon and Green, they show that even liquidus does not react if in the system included methane. So I believe that this dropping of diamondiferous kimberlite also possible to explain the increase of oxygen fugacity of mantle fluid during geological time. And you see that scale of such subduction material enormous. This is a Farallon slab. So I believe that it is must influence to the fluid, mantle fluid. And what about plume connection? So first of all, I showed that isotopical signature coincide with the Fozo reservoir, which is considered as a plume signature. And second, generalization of recent data on seismothermography showed that showed the existence of three global, look at that, global area which was called plume generation zone. This zone situated on the boundary between core and low mantle. And about 5 years ago, Torstvik plot all lips, large igneous provinces, and kimberlite on these three zones, and as a result of paleo reconstruction. When I read this paper in Nature, I was very excited and tried to find a person who can make paleo reconstruction of alkaline rocks and carbonatites. And I was very lucky to meet Roman Veselovsky, and we together with him plot all carbonatite, and look at that. They also controlled by marginal zones of this actually mostly African plume system. And Kola plot somewhere here also belong to this system. So in Devonian time, Kola situated here close to equator. But also interesting that practically no carbonatite here. Probably the thick lithosphere is necessary condition for the forming of alkaline rocks and carbonatites. So I think my time is very far. So I would like, collectively, I would like to stress that I think the most important This is the uprising plume and partial melting result of adiabatic decompression and metasomatic process which very close connected to blue system. Thank you for your attention.
Thank you, dear. Please, one or two questions, no more. No questions? Okay, thank you. I think the further questions we will move to coffee break. Okay, so see you back in 20 minutes.
А я сейчас могу листать вообще?
Там, вот там следующий слайд был, да. Вот этот. То он в какой-то вот в этот момент начал тормозить. Ну все, то есть сейчас все хорошо.
А это чья? А чья это?
Нет, 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 то, что я вам утром показал. Там AV файл. Ну, у тебя заработало? Так. 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 Вот, вверх. Еще. Вот здесь вот, назад. А где? Нет, там была картинка. Дальше. Вот здесь должна быть.
Но его здесь нет, я его отдельно тогда включу, видео.
It is not my paper, sorry. Maybe we will wait a little bit, because it's empty space too much here. Да, подождем. Тем более, что мне ничего не показывает. Следующий доклад загрузите, пожалуйста. Но, не этот. Я могу, конечно, Колин сделать доклад, но я его не знаю. Это будет Но. Не этот тоже. Этот я не буду делать.
Как он называется?
Соболев. Программу, им надо программу дать.
Okay. Another claim. Alexander Sobolev, Vernadsky Geochemistry Institute, will talk about the temperature and water contents of mantle-derived magmas and their sources.
How it's working?
Oh, it works.
Центральная — это указка.
Good afternoon. First of all, I would like to express my gratitude to Professor Gagarka, who invited me here. This is a general talk on vast issue, and a lot of people contributed to that in different aspects. That is a list of these people, maybe not full. I will talk about melting anomalies in the mantle and how to explain them. Yes. So melting anomalies. You see here on their blue background a lot of colored features, which are in fact residual tomography in kilometers of significant increasing of crustal volume in the oceanic crust. They are all melting anomalies, of different scales. And also you can see there these bloody red areas on continents which are large igneous provinces on their continents we have heard about this morning. These are also very large melting anomalies. That is the Atlantic sector, that is Pacific sector. So that is a global event which need to be explained. And certainly explanations are well known. And these, the most common one, are called mantle plume theory, goes back to 70s and the name of William Jason Morgan. And very shortly, that is an example of mantle plume for Hawaiian track, where Hawaiian islands present a track of islands which produced by moving of lithosphere over stationary mantle plume staying here. That is a classic example of this mantle plume theory. And here, on this complicated figure, on the left side, you see this essence of this plume theory when hot material is coming from the boundary between outer core and lower mantle from a huge thermal boundary layer, which is placed here. And this material transfer heat to the surface, producing melting anomalies and significant temperature excess compared to the temperature of ambient mantle. That is a classical view, and that is another extreme which could explain many features of melting anomalies based on the concept of mantle heterogeneity, where compositional anomalies in the mantle can produce similar effects that temperature can do. And indeed, experimental petrology tell us that addition of fertilizing elements to the mantle peridotite indeed could decrease significantly temperature of melting and production of melt at the same temperature. So potentially that is a very possible explanation, especially if you add water and carbon dioxide to this story, which are significantly decreasing temperature of melting and increasing melt production at the same temperature. That is shown here on the ground of comatiad problem, where you see here Archean comatiads, if they are hot, could be plume origin, if they are hot and dry, and if they are wet and less hot, they can be upper subduction origin, and that is a very significant difference between these two regimes. So potentially adding water will transfer hot spots to wet spots, and that is another way to contradict mantle plume theory. Yes, not. Okay, so the problems which I would like to address here, questions are listed here. First one is, how hot are melting anomalies compared to amphibian mantle? That is an important question because the only way to recognize plume from anti-plume theory is significant difference in the temperature between melting anomaly and ambient mantle. 100 degrees is not enough. We need more than 100 degrees, 200 degrees and more. That is direct evidence of plume over not plume theory. Another thing is how hot or wet are komatites, and then how hot, wet are suprasubduction magmas. And these three questions are wide enough, but you will see that during this talk we will come to even more wide questions, which are listed here: when plate tectonics has started at the Earth, and what is the origin of Earth's water. So, the way to estimate source temperature is listed here. A lot of people have tried to do this using iron-magnesium partitioning between olivine and the melt, or major elements composition of the melt, or composition of peridotite rhystites. Many papers, but all one general assumption: periodic mantle of known composition and known independently water or carbon dioxide content in the melt. Without this assumption, this is not working. Not easy to, but, right, but. How good is this general assumption? Probably not very good, because we know that subduction indeed takes place, and indeed it transfers a lot of basaltic component to the deep mantle, and that is a very different composition, which could produce, and probably producing heterogeneities, and you cannot apply a normal way to calculate temperature of the mantle for these kind of materials. Also, you have to know what is the water content to estimate temperature. And that is also not easy question, because Park sands and amphiboles and pelagic glass thermometers and hygrometers, which are commonly used in many cases, are not useful for primary melts, because these minerals are never first in mantle-derived magmas. Also, direct water measurement in glasses do not work for high water contents because of degassing. And direct water measurement in melt inclusions are more reliable, but could be compromised by hydrogen exchange through the host olivine. For instance, this paper of Partnagin and others, many others now. So thus we need to measure temperature and water contents of primary melts independently. And only if they fit each other, that is a reliable answer. So the way to do this is to look on the olivine, and in particular to look on the elements which are very slow in diffusion in olivine. And that is this area, which are phosphorus, aluminum, chromium, or maybe some rares and yttrium. And these elements, partitioning of these elements between melts and minerals with olivine, could be slow enough to present magmatic temperatures. So, and indeed, there is a good thermometer, olivine spinel thermometer, which was introduced first by Van et al. And later summarized by Coogan, which is based on alumina partitioning between olivine and spinel, and this kind of equation with quite good precision. However, it is restricted to low titanium spinels, low chromium, well, not very high chromium in spinel, and temperature range here, and highly reduced condition. And that is essential. These are essential restrictions because you will see here, what? You will see here a chromium number and iron. Well, iron 3 are number in spinels of this experimental database, which are shown here, compared to Kamenetsky and et al. Database of natural spinels from the mantle-derived melts, which are here. So you see almost all the data which are the base of this thermometer are lower in iron 3 compared to natural spinels. And that is a significant difference, especially for suppressed subduction magmas, which are over here in this area. The same restrictions are for titanium-rich magmas. You see all the data, experimental data are here, and titanium-rich magmas like Siberian memiches, for instance, are here, out of the range of this thermometer. And that makes us, that stimulates us to start our own experiments to produce a new version of this thermometer, and we use this setup, experimental setup in Vernadsky Institute, which you will see in more details in a paper of Krasheninnikov, who will present this today. So essentially, we can go to very high temperatures with buffered oxygen fugacity. And our experiments in one experiment, we are doing up to 6 different compositions. Each composition, after quenching, have glass, olivine, and spinel of very equilibrium compositions. You will see this in the presentation of Krasheninnikov. And our set of spinels are now much better fits natural field because we use condition for oxygen fugacity from nickel-nickel O -2 to nickel-nickel +3. So 5 orders of magnitude oxygen fugacity. So better fits for iron and better fits for, well, what is that? Supposed to be titanium, sorry. Something strange. It's Mac Windows tricks. Okay, so that is the more important. Our thermometer, which is shown here, fits very nicely our data and data of Coogan and all others. In one equation, we fit all the range. And in addition to this thermometer of Coogan, we have now what? Yes. We have now this equation, which take into account titanium and iron 3 components, which are very strongly affect temperatures. And with the same precision, we are covering all the data sets. And I can show you now how it's working on the example of Icelandic olivine from Picrite. That is glass, that is olivine. containing inclusions of spinels here, 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 here. And that is iron map showing more magnesium-rich core and iron-rich rim. Please take into account this spinel right on the interface here. So these are also spinels here of different compositions. So now this map of alumina. Alumina zoning is much more complicated than iron because it is much slower than iron. What do you see here? Our spots around spinel. We analyze olivine and calculate temperature using our thermometer. That is the standard deviation of these 4 spots and so on. And what do you see here? The range which we are getting from one phenocryst is over 140 degrees C from the center to the rim. And that is a checkpoint here. That is a temperature obtained from our thermometry, and that is olivine melt iron magnesium temperature calculated from the glass composition. So this checkpoint is nicely show you that both thermometers fit each other within an error. So you can see that indeed high magmatic temperatures are frozen here in one phenocryst composition. So now we are doing the same job for all olivines from different geodynamic settings, starting from mid-oceanic rich basalt. That is the first right, that is the temperature calculated from this approach. And that is a fast spreading rift systems. These are slow spreading rift systems. And these are ultra slow spreading rift systems. So that is a Knipovich ridge actually. What do you see here? That is a range here. That is a Morp field here. Strange, I'm missing some points here. It's strange, wow. So these islands, this Iceland, which is higher than Morp, with some interaction, and the interaction here is Reykjanes and Teistorykr rifts, which are south and east and north north connections of Iceland to mid-Atlantic ridge. That is Hawaii, hotter. Even hotter, these are West Greenland, which are beginning of North Atlantic large igneous province. Wow. That is even hotter, the most hottest, the most sort of phanerozoic magmas are Gorgona picrites, which are part of large Caribbean large igneous province. And finally, hope so, it will appear sometime. Yes, Siberian mimiches are here. So the most hottest are part large igneous provinces. You can transfer these eruption temperatures to the mantle temperatures using the hottest, yes, the hottest are indeed Archean komatiites, which goes up to large, very high temperature. You see Mac Windows tricks. Okay, so we can transfer these eruption temperatures to mantle potential temperatures using known procedures. To be short, I will tell you that just mantle temperature is always higher than eruption temperature because of temperature drop during adiabatic decompression and because heat loss during melting event. If you take into account all these things, you will get temperatures in the source, potential temperature in the source, which are proportional to the temperatures, eruption temperatures. And what you see here, Phanerozoic ambient mantle, which is our MORP source, with this lower outlier, which is USSR MORP Knipovich, that is a cooling effect of the lithosphere. We will not talk about this here. That is typical upper ambient mantle. And all plumes are indeed hotter. A little bit like 100 degrees for Iceland, 200 degrees for Hawaii and Deccan, and hotter for Phanerozoic are large igneous provinces. They have over 200 to 300 degrees difference with ambient mantle. Komatiites are even much hotter. So now, if we know temperature, we can estimate water, comparing known temperature and calculation for the dry and water-bearing system of the same conditions. So that is for Abitibi komatiites from Canada. What you see here, they are not entirely dry. They are a little bit wet. Maybe we can see up to 1% of water here. So we detect some water by this procedure. Well, here are many suprasubduction magmas. Starting from Cape Fogel Bodinites, Tonga Bodinites, New Caledonia, and Skruchevskoye volcano. All they are wet, significantly wet. They show water down to up to 4% and more. If you now calculate mantle potential temperature for these magmas, including suprasubduction setting, you will compare to ambient mantle, you will get, again, mantle plume, as I showed before. And you see many of these suprasubduction magmas are within ambient mantle temperatures, but some are higher. For instance, Camp Fogel and Troilus are higher, which implying that mantle plume was probably one of the source of component in these particular areas. And that is fit very well the model of plate tectonics triggering by plume, which was published 1 year ago by Gere et al. So the source of water, which we see directly in suprasubduction magma, is well known. It is descending lithosphere slab. And what you see is happening here, that is a classical sketch for suprasubduction setting. But what about komatiites? For komatiites, story is different. That is a paper which we just published on the komatiites for Archean komatiites from Canada. And in this paper, we did high temperature experiments in Vernadsky Institute, made electron probe analysis in France, and ion probe analysis in France also, and laser in Germany. So it's big international effort. And it was supposed to be a video showing quenching of our inclusions from very high temperature in a fraction of a second. These are inclusions which are produced by this quenching, which are nicely glassy or even are homogeneous. Homogeneous. These are forsterite temperature plots showing that water content measured directly and calculated by difference between independent temperature estimate and modeling of dry and wet conditions show the similar results, and these results show that the water in the primary malts of these comrades is indeed high, much higher than was expected before. And if you plot now this on their spider diagram, where that is ratio of element in the primary malts to bulk silicate earth, you see very significant features here. Here I compare suprasubduction typical refractory malt from Mariana with our parental malt here. What you see here is these three very high anomalies. The highest is water. That is a similar feature to suprasubduction settings. But what you see here, this is very different from suprasubduction settings. You have no any signature of suprasubduction on this element, which should be here and seen very well in the Mariana of Iraq. And that's drive us to conclusion that that is not suprasubduction setting, and we have to find other source of water compared to elements of the same impeccability. And that is, we think, transition, which is shown here. That is a boundary of olivine Weiss-Delete transition, Weiss-Delete ring-Delete transition. These are the same olivine composition but different structure. And what is essential, these Weiss-Delete and ring-Delete, they could contain a lot of water, like 1,000 times more water than normal olivine. And in this cartoon by Pearson et al., this water is coming to this zone by subduction and accumulated here. And we suggest that our source of water is transition zone, and we get it in our commodities from here. And that means that we can estimate water in transition zone using our data. But first of all, that is the data of Pearson et al. 2 years ago, who analyzed ringwoodite in a diamond from Brazil. The age is unknown of this ringwoodite, or it is more than like 100 million years, because it's the age of kimberlite, which transported this diamond. And what they calculated the water content of transition zone using this ringwoodite, and it was 1% of water. And if you now apply different models for the mantle, starting from primitive or depleted or early depleted reservoir, you can calculate water to cerium ratio, which is the ratio of elements of similar incompatibility. And that will be this range here and this range here. So our point for Canadian commodities is here, well-known age, and water to cerium ratio is similar to the range of that. So the problem is now, should be here, yeah. So either this subduction, well, what is the source of this water? This is old water. We found that at the old time water was there, so it is or high water from the accretion or very early subduction, which took water inside this area here. Okay, so To check this, if it is to find out what is valid from these two hypotheses, we have to go to earlier ages. And that we did right now. 1 month ago, we got the data. I presented here the first time. And that is the data on our Wilterfreden part of Barberton Greenstone Belt of 3.3 billion years old. So what we have now, yes, Komatiites. Yeah, we got strong correlation between composition of host olivine and water in these melting regions. And this strong correlation is ended that should be 96, which is the most magnesium olivine here. And that is our prediction for the primary melt here. And if you look on other elements, well, you can recalculate this to MgO in the melt, that is around 30%. And you see very nice olivine fractionation on major elements, like alumina or silica. But what you see here, what you see here, the water is not feeding olivine fractionation. You are gaining water during fractional crystallization. And you are getting not only water, you are getting chlorine and potassium. Potassium, that is olivine fractionation plot. So you're getting potassium, you're getting chlorine. So you're getting water, seawater altered material in an AFC mode, like assimilation fractional crystallization process. And that means that that komatiites which are significantly evaluated, low magnesium olivines, they could be significantly contaminated by water, and there is no way to estimate primary water content using these numbers here. You have to go to very magnesium olivines to get these numbers. And this number is now here. So that is lower than our ABTB one, and that may suggest us that it was really subduction story, and that fits very well with uranium depletion ages of the well-known periodites, that is a Parman compilation, or, well, that was yes, that is the same very well fitted epsilon hafnium ranges, which was shown by Kostitsyn yesterday. So I think that may be a good sign of early subduction rather than high initial water in the Earth's mantle. That should be, of course, proved by additional data on other ages and other places. So to take home messages are here. First, canonical mantle plumes and large igneous provinces do have high potential temperatures compared to MORP sources, at least on this range. And that proves mantle plume theory. Potential temperature and high water contents of suprasubduction mantle sources confirm origin of suprasubduction primary mass by water fluxing of convecting mantle wedge. However, some exceptions, which are bonnanites from Papua New Guinea and Troilus, which require high temperature and plume-related sources. Ultra-high potential temperatures like that and moderate water contents like that of komatiites from Abitibi, Canada, suggest their plume origin and attrapment into the komatiite source of hydrous material from the mantle transition zone. And compared to data on ringwoodites, age is unknown, and abetibicamarite. Of this age, sources, the source of Welterfred camarite of Barberton greenstone belts of this age was less enriched by water, which implying drier transitional zone. This may suggest early start of plate tectonics on the Earth and low original water contents in the Earth's mantle, but it should be proved by additional data. Thank you for your attention.
Thank you. We have time for several questions. Please.
Well, very recently, a year ago, it was a paper of Geria, Stepan Sobolev. Yes, but I think it no. Well, a chicken egg problem. Well, I think what they show that large plume significantly increase probability of thickening of lithosphere and producing subduction. So their point of view is that plumes were indeed triggering mechanism and the course of first subduction appear. I think it's very well suited with the data we have. Maybe plumes like comarites, which are plumes indeed, they made starts of this convection of this subduction early in the Earth's history, probably at around 4 billion years, and that started all this engine.
So in Archean, mantle was water went to the decay by 200, at least 200 K.
Yeah, right.
Then plumes were hot, but the difference with the environment was not so hot. This is the first point. So my impression is that this example of the Caribbean basin is okay. You can start from the subduction with a large plume, but it should happen in Archean. Because otherwise I can't understand. If you have small difference between the temperature of the plume and the surrounding mantle, how can you get this much effect of subduction on the surface?
Well, first of all, it is not small. Temperature difference is high enough. In our calculation, it is at least 150 degrees C, at least. In Archean, probably even more, a little bit more, up to 200 degrees. So there is significant difference in temperature. And we had consulted, I had talked about this with Steve, and in their model, it works well. This difference of 100 degrees over the 100 degrees is working well with their model. So what they agreed, our meteorological results are working in Archean to start plate tectonics as well.
Okay, Pierre,
Pierre,
will be next.
Yeah. Yeah, okay. Good question. I would not believe just on water measurement in multi-occlusion itself, because water can could gain from outside or bend out to outside. That happens in hours. So that's why in our paper we take two two independent observations, temperatures and water. And because they fit to each other, we are confident that that is indeed reliable data. So our temperature is not high enough to be dry for komatiites. So it is exactly like 50 degrees lower than it should be from the dry source. And this corresponds to 1% of water. And we get this 1% of water by direct measurement. Together, this is the same results showing that all this story crystallizing and quenching was very fast. And water was not, in this case, lost from inclusion. Today, you will get another paper of from our team. Name? Nazarova? Yes. She will give you evidence that water was indeed lost from inclusion because temperature is lower than water suggestion. Temperature suggests more water in inclusion than is observed.
Okay, I'm sorry, but last question to Lee Kagarka.
One argument in favor of plate tectonic structures on the boundary archaic Proterozoic is that there are no diamonds older than
3.7. Well. So, if you mean this paper of Carnegie Group, that is enough. So, it is like it is around 3 billion years. I think even more, 3 point something. Yeah. Yes, at least 3 point something. There was subduction because they show that it is like ecologic source, which Pierre will not agree. Anyway, but well, statistics is very low actually. Yeah.
Okay, I think we can continue to discuss during breaks. And now time for next talk. Sorry. And next talk of Alexander Samsonov, IGEM, about Paleoproterozoic history of Eastern European Craton.
Probably more than half of lithospheric Earth were formed during early Precambrian time, and now it is present as small tectonic fragment in the different continents. Richard helped me and make introduction to paleotectonic reconstruction, to problem paleotectonic reconstruction in the early Archean. And you can see that for 1 billion years ago, Rodinia, it's more or less clear, and more or less clear for end of Paleoproterozoic. But a lot of questions there are when we come to beginning Paleoproterozoic into Archean. There are questions what kind of supercontinent or different supercraton was, and question about how the continents remake and move. You can see that this more clear reconstruction include tectonic fragment where each fragment present tectonic slice of
much more block. And in my talk, I will try to show you problem of tectonic reconstruction. The example of Baltica, you can see here, here. And we know Baltica more better as East European craton, basement of our East European platform. East European craton is not good exposed. Only two big outcrops in the north, it's Baltic Shelf, and in the south. And all other territory is covered by thick platform cover. And we are here now. And it's defined the problem, tectonic discussion about tectonic structure of this craton. And you can see how very few deep drill holes which open, which reach the platform basement. And main reconstruction make on the geophysical data. And all the summary, all the most important input into reconstruction of East European craton make Svetlana Bogdanova. You can see first big work here. It's about Volga-Uralia. Then Svetlana studied Finascandian again, now studied this area. And his model, based on geophysical and drill hole samples, allow her to recognize three large different blocks within East European craton, Sarmatia, Volga-Uralia, and Finascandia, and separated them orogenic system. This model was proposed first time in 1993, and up to now is good enough and allow us to explain all data which we obtain. The object of my talk is the tectonic history of East European craton, based mainly on the result of study, dating isotope study of drill hole samples, but together with geophysical data. Some words about Archean megablocks. There are three Archean megablocks, Finascandia, Volga-Uralia, and Sarmatia. And Finascandia and Sarmatia is well studied because it's open on the shield, in the surface. And these megablocks have quite different history. If we see Sarmatia is so-named Valbara type block, very old Paleoarchean core, and beginning of Paleoproterozoic, non-magmatic, and sedimentary with large beef sediments. You know Kursk anomaly, it's this part. And adjacent Finascandia, quite different. You can see main crust-forming events, Neo-Archean, and all Paleoproterozoic this time is a lot of magmatic events, probably related with lip or with plume events. Volga-Ural is not so good studied, but it is similar to Finascandia rather than Sarmatia. Paleoproterozoic belts, which separated Archean blocks, is not so good studied because most of them closed, covered by platform sediments. But Svetlana Bogdanova believes that Riphean rift system were formed after the Paleoproterozoic orogenic system, and on the basis of this, they proposed this boundary. And now, when we study history of formation of this territory, we obtain evidence that it was right preposition, that was right hypothesis. There are four main orogenic, Paleoproterozoic orogenic belt, Volga-Don, Central Russian. You can see also system rift, white, Lapland Kola, and large Svicophenian. I will shortly show you the new data, when new data we have. Volga-Don origin was studied last some years. A lot of new data. What we know? Very short subduction-related volcanosedimentary sequences, which form all this green area. Then short collision system, which dated by monazite in this part of the origin, and by dated of zircon in this part of origin, the same time, and and post-collision, post-tectonic magmatic events, also very short, and all the systems have such short history. Это что? Ау. In compare with Volga-Don origin, middle Central Russian origin is not exposed at all. And all the data, it's geophysical data and study of drill hole samples. On the geophysical data and using samples, we can recognize several different blocks within such transection of this belt between Karelian or Finascandia craton and Volga-Uralia craton. Different age from south to east, you can see Paleoproterozoic, Archean, Paleoproterozoic, Archean. Moscow belt. You can see many samples, mainly Paleoproterozoic. Rocks consist of amphibolite, probably metavolcanic, and different granitoids with island arc geochemistry. And one data, zircon data for granulite from this part nearly 2 billion years ago. Very important that all the rocks of Moscow belt is very similar to the rocks of Osninsk-Mikashevich belt, which well studied on the part, on the boundary of Sarmatia craton. You can see similar granitoid, similar mafic volcanic, and epsilon neodymium values. So we can say that it is a wall, a single magmatic belt, which was formed as active boundary on the Volga-Sarmatia megablock. It is more later than Volga origin. Next, Tver and Yaroslavl block, Archean block within this belt. Here you can see Tver more older, Yaroslavl younger slightly, but it is all Archean. And Tver block is very similar in age and geochemistry as adjacent Vodla block of Karelian craton. So it's look as boundary of Karelia. In composition of Yaroslavl and Tver block, there are two main types. In Tver block, granitic gneisses, it's host rock, metasedimentary rocks within Yaroslavl block, and very unusual rocks, high titanium, high ferrum intrusion within Tver block, and high titanium gabbro within Yaroslavl block. Uranium-lead data of zircon suggests that this block is Archean, Yaroslavl, and Tver terrain, but intrusion of high titanium intrusion is 2.5. It's beginning of Paleoproterozoic. And that is important. It's geochemistry of this rock. That is important 2.5 intrusion within Tver and Yaroslavl blocks is very similar to high intrusion, to high titanium intrusion within volcanic passive margin Phanerozoic age. And this probably suggests for tectonic setting, suggests that it is passive volcanic margin. Rybinsk belt, small belt here with mainly Paleoproterozoic source. It's metasedimentary rocks, and these metasedimentary rocks quite the same as adjacent sedimentary rocks on the Baltic Shelf within Raahe-Ladoga zone. It is typical sedimentary passive margin reconstructed here and probably also here. All the data suggests that source was very close. Short conclusion for Central Russian belt is here. I told about it. Osninsk-Mikashevich is single belt 2.0, 2.5 OIB-like intraplate magmatic events maybe suggest volcanic passive occurrence on this time. And boundary between this part and Moscow igneous belt were formed between 2.0 and I forgot to tell metamorphic events 1.75, and these sediments, this rock and this rock probably give us sediments to the adjacent Rybinsk terrain. Next origin, Lapland Kola, and probably Dwina origin. Dwina is a continuation to Arkhangelsk region under the platform sedimentary. You can see that all evidence, tectonic evidence, Avlokagen is here, but it's a picture, tectonic picture for this area, and large Archean blocks is shown. I believe that is shown because here is Arkhangelsk kimberlite. If we have kimberlite, that basement crust must be Archean. But it's not quite right. Lapland Kola again is well studied in this area. It's typical collision structure. It's morphogate data. And if we will see in this area, in geophysical field, in geophysical map, you can see that this structure is have continuation here, and that is very important. There are some deep drill hole which open, which reach the basement of this area. Belomorian belt, you can see Archean chest part. It's epsilon neodymium model H. All granitoid and sediments in this part is Paleoproterozoic. Only Tsenagora drill hole in this part is also Archean. If we we have dated 2 or 3 samples of granitoids, and age of granitoids nearly 2.0, but what is very important, 2.1, 2.1 inherited zircon. It is probably zircon from matrix, which from sediments which include this granitoid. The same picture, similar picture, we can see from xenolites, from kimberlites. Crustal xenolites, very similar in model age as rocks of basement. So we have some evidence that not only here, not only on the surface, but also in the deeper part, it is all Paleoproterozoic. But in Griba pipe, we find some Archean xenolites, which suggests that there are heterogeneity of crustal cross-section under this area. Very interesting and important data was obtained from zircon xenocrest, from porphyric kimberlite. You can see that in this area, it's Pionierskaya from Zolotitskaya field. no Archean at all within Xenochrist zircon, but a lot of young zircon, 1.5, 1.2. Rock of this age is not known here. The same situation here, but in Griba as well as for xenolytic rocks, Xenochrist of zircon also show us Archean basement. All the data allow us to suggest that it is a single collision origin, it is tectonic structure of origin using morphoGT data, and it is probably, possibly tectonic cross-section using data from surface and from xenolites and xenocrysts from kimberlite. Fourth origin, Finascandian origin, is very good studied in Finland, in Sweden, and Norway. And history from 2.0 before 1.8. It's very, very nice studied collision, accretional origin, which were formed nearly western part of the Archean Finascandian blocks. Short summary for Paleoproterozoic tectonic history of the East European Craton is in a simple picture. For the time 2.5 and before, there are data that Sarmatia was far away from these blocks, and no evidence that Volga-Ural and Karelia was far away between. So, two different Archean blocks. Between 2.5 2.2, Sarmatia is also far away, and Karelia probably begin, not Karelia, but this block begin to broken. Data for this is volcanic passive margin 2.5, and it is possibly also in this time was broken and separated Karelia and Kola Murmansk Craton. Next stage, we can see that Volga-Uralite Sarmatia begin to move and plate tectonic system begin to work between there. And at the same time, probably begin to open volcanic system in the Svicaphenian Ocean. Next stage, passive margin, volcanic island arc system here, and collision and post-collision stage here. And this stage, formation of Moscow Osninsk-Mikashevich belt active margin on the Volga-Sarmatia belt, but no any subduction in this part. And in this stage, it's Svicaphenian Ocean finished, and it is fragment of our platform which we study to discuss. And conclusion. If we look at the tectonic map of the East European Craton, we can see that all kimberlites located within Paleoproterozoic origin, but not within Archean craton. Arkhangelsk, Yermakovka, Finland, two system of Kimberlitic, Neazov, and also Kirovograd. Maybe diamond-ferrous roots were formed when Archean crust, Archean lithosphere was moved to the depths and formed the root by this way. Thank you for your attention.
Thank you. Questions, Ilya?
I know from colleagues located in Perm that there has been a long-standing discussion and problem about the source of diamond places in the north of Permian region. According to your ideas and reconstruction, could there be any kimberlite pipes in that region, or they have been transported somewhere from Arkhangelsk?
I need to see.
Okay. Lee,
1.7 was very big metamorphic event.
Yes.
Yes. How big it is and what was the reason for that? 1.7.
Is it possible?
Doesn't work well.
No. Yes. 1.7 event is really very fixed in many places, yes. But if we look within Archean blocks, we cannot find to 1.7, only boundary part. 1.7 is event of collapse of large Paleoproterozoic origin. And this collapse give, in this part, it's slight tectonic, and in this part, it's сдвиговая тектоника. But usually on the boundary between Archean and Paleoproterozoic. It's especially.
okay, Richard.
On the western margin of Karelia, you were having opening at 2140, 2.14?
Here.
Yeah, and what was the basis for that?
If we will see, if there are ideas that this ocean was open 2.06 or 2.1, yes? But we know that there are many zircon within Lapland Cola origin with age 2.1. It's suprasubduction source, and if ocean open 2.1, it's impossible to explain where, no time to initiate and to make subduction-related rocks here to give this zircon, here is also in the Arkhangelsk area. Also, 2.1 zircon, a lot of.
Yeah, but on the west side there, I guess I was going to ask, would not it be reasonable to
West. Aha.
to open it at 1.98 to 1.95.
I do,
Tie it into the magmatic event that is present from Pechanga down to Onega.
I understand. There are two explanations. First of all,
But I mean on the west side, I'm not talking about the Lapland side, I'm talking about where you say Fennoscandian Ocean. That's the side I'm thinking about, not the between Kola and Karelia. I'm not thinking about that side, I'm thinking about the other side.
let's later.
Now, Levo is sort of there. Again, it's in the Fennoscandian Ocean.
Yes.
Открывает 1980.
There are 2 points. There are also 2 points of view when it is open. First of all, 2.1 is active passive volcanic matter. Yes? And another 2 point.
Connected still, 2.1, this was still connected to Superior. We have a map here, Osiasin, 2.1 to an event in Superior Craton. So it's still, things are still connected. But I think there's a big magmatic event at 1.98 that is widespread. And on that,
One point. We have. Yes, I understand. We have also here and here at this event.
But I think a reason for connecting it to the western side is that you also have the Jorma and Oricompo.
Jorma is younger.
Little younger.
It's 30 billions. It's enough. It's not related. No.
Okay, it's another discussion for break. Yeah, you can continue during lunchtime, and we have 2 possibilities for lunch. One, we have small cafe just downstairs here, and another is large cafe in Moscow State University building, 100 meters across the street.
We are apparently late. Shall we wait for some 5 minutes? Dr. Zaitsev, could you please call others here? While we are waiting, пока мы ждем, вы не можете поставить следующий доклад? Это доклад I.S.E.S. Поставьте, пожалуйста. Nobody left? All are here, right? Okay, so Andrei, please. Now we are a little bit late, but we will try to be on time more or less. The next talk is by Andrei Zoch from Sobolov Institute of Novosibirsk and State University of Novosibirsk, I think. Evolution of the low titanium lamproid magmas. Tabuksky.
I changed the name of my report,
Okay,
and I tried to show you evolution of low titanium lamproid from Vietnam and from Aldan Shield. And the history. The first who name describe high potassium rock was Nigli, but he not name it as lamproid. And when we with Alexander Sobolev learn in Novosibirsk State University, we do not learn lamproitic, komatiitic, or bananitic rocks, because they was named and discovered sometime later. And therefore, for young men, some description of lamproitic by Mitchell, it is international classification of lamproitic rocks. Sometimes describe only high magnesium and name it as lamproitic rock, describe the series of rock as lamproitic series. And therefore, mineralogical criterion of lamproitic is high titanium, low aluminum phenocryst of phlagopite, sometimes tetraferroflagopite, and tetraferroflagopite may be in grain mass of these rocks. Sometimes potassium richterite as mineral which describe if in high titanium lamproitic, but in low titanium lamproitic rare we can see richterite. Of course, high magnesium olivine in lamproite, it's good features. And diopside, low aluminum and low sodium component in diopside. In leachite is one of the ways to lamproitic, but in more we have asanidine. The presence of primary plagioclase, if we have primary plagioclase, magmatic plagioclase, we cannot possibility classify these rocks as lamproitic. And chemical criteria of lamproitic. High concentration of potassium, high concentration of alkaline, and these rocks are per alkaline. And typically, high concentration of calcium and two types of lamproite, low titanium and high titanium lamproite, and high concentration barium, strontium, zirconium, and lanthan. We investigate these rocks in North Vietnam, and this Fancy Pan uplift where we investigate low titanium lamproite. Lacroix named this rock as cassite, but it is not correct name because he described this rock near Cockpit village. I tried to look these outcrops, but now it is not village, it is town. It's not possibility to see this little body. And we describe this high potassium paleogenic and ultra high potassium alkaline rocks in our book with Vietnamese colleague, which in this year published in Springer, Interplate Magmatism and Metallurgy of North Vietnam. In this chapter, we can read some information about this interesting rock. Location of cassite is in Fancy Pan outlive, some place where we can see little body, dikes, and often only stones in river, because outcrops in Vietnam are not good, and we can not possibility to see all association, because only a part of this system we can see. For example, it is little intrusive body which described by Lacroix, Cockpia intrusive, and now we can not see this body. The petrography of these rocks, we have phenocryst of high magnesium olivine, subphenocryst of diopside, phlogopite, zoning phlogopite. The central part is tetraferriphlogopite, and this part is phlogopite. And in grand mass, we can see leachite. Sometimes we can see zoning diopside too. Chemical features we can see on this slide. there are high potassium, some rocks are high magnesium, and we have the serious rocks from olivine lamproite to minetta, and last stage is cyanide porphyry. But titanium in these rocks is low. It is Spanish type of lamproite or Mediterranean lamproitic rocks. Distribution of rare earth element from different places of North Vietnam are the same, and the same features of these rocks we can see in Aldan Shield. The location of these high potassium rocks connected with Allow Shine Retriever shear zone when India collided with Eurasia, Indochina block come to the east, and the distance more than 700 kilometers. And the age of these lamproitic rocks, 35 million years. It's young. What is interesting is that in China there are some large rare earth deposits which connected with alkaline cyanide, and the age of these deposits the same to lamproitic rocks. And Chinese geology decided that this carbonatite and buried fluorite carbonatite veins connected with evolution of Nordmarkite. But I do not agree with this model, because we do not see some carbonatite in Nordmarkite. In the type of this ore, it is buried fluorite carbonate veins, breccias, and some people said that it is not magmatic, it is hydrothermal event. But inclusions in this in fluorite investigate melting inclusions. In Vietnam, we can see the same deposits, more small than in China, which sit in cyanide. But in this region, we obtained some lamprophore and lamproitic lakes, and we connected this fluorite and carbonate breccia associated not with cyanide but with lamproitic rocks. But in Vietnam, we have not possibility to understand what kind of evolution this high potassium rock. Therefore, we investigate this rock in Aldan Shield, where in Mesozoic time there are interesting high potassium provinces, and we can see Rябиновый cyanide massive is copper, molybden, and gold deposits. Inagli donite massive with platinum mineralization. Seligdar is more older. Ilya Prokopiev said tomorrow that it is more old. And in this area, Vladykin and another investigator describe lamproitic rocks too. We investigate a lot of dikes from Rябиновый massive, in one small line, not bigger than this hole, we can see olivine lamproid body, we can see shankinite or pyroxene phlogopite lamproid dakes, different dakes of minette, and cyanide dakes. And one dakes of mingling between cyanide and shankinite porphyry. And therefore, we can see that the age of these dakes 125, but the cyanide from Rябиновый массив more older, то есть, как говорится, 137. And we can see the first stage is olivine lamproid, breccia, and dakes with fresh olivine. Then in olivine lamproid we can see some xenolite of glomerite. The next stage of dakes is minette dake with flow differentiation. In central part, we can see a concentration of phlogopite phenocrysts. And in minette dake, we can see some carbonate, fluorite, and feldspar bubble, and we decided that it may be liquefaction between silicate and carbonatite melt. But it's not a good example, of course. We have composite cyanide dake, melanocyanide, leucocyanide, and we have possibility to understanding what kind of evolution parent magma in this area, because this dake connected with the deeper chamber, and therefore we have possibility to see how evolution of parent melt. Chemical composition. All rock is subalkaline or alkaline. It is olivine lamproid, minette, and cyanide. Some cyanide porphyry part in this part, but these dakes have a large amount of carbonate, therefore low chromium. Here we can see that it is one series of rock. Olivine, lamproid, minette, and cyanide. In calcium, we have low variation in magnesium part and in cyanide part, but in minette we have high dispersion of calcium, and we propose that it may be connected with silica carbonate liquefaction. All rocks are high potassium. You can see the ultramafic rocks are more high potassium than cyanide. And low titanium too, the chemical features are the same to Vietnamese lamproid. It is low titanium lamproid series. Rare earth elements, we can see on this slide high concentration of lanthanum and cerium, low concentration of heavy rare earth elements, absence of europium anomaly, and more interesting that cyanide have low concentration of rare earth elements than minette. And it is unusual because if we have differentiation of silicate melt, cyanide must lay upper to the ultramafic or minette dikes. I try to show why we have a low concentration in some minette dikes, or some cyanide. Because we can see this in petrography of these rocks. We have fresh olivine phenocrysts in this rock. It is the same to Vietnamese lamproitic rocks. The composition of olivine very high magnesium and high nickel concentration in olivine, and this high magnesium olivine in the central part of phenocrysts, this the room of phenocrysts. And chromite inclusions in olivine in central part, we have magnesium chromite. In room, we have chromite. Therefore, we have evolution of olivine from central part to the room of these phenocrysts. The grain mass, we can see zoned diopside crystals and zoned phlogopite crystals, and this one, it is feldspar. This may be distinguished as leachite, but now it is the phase near analcime, not leachite. Another rocks, another dikes, have phenocryst of diopside, but in central part, when I describe petrography of these rocks, I decided that it is chrome diopside, but it is igurinavgit. And this is diopside. It may be phenocrysts of igurin diopside from cyanide, another that we have mixing between different stages of evolution, these lamproitic rocks. This one is phenocryst of apatite. Composition of this pyroxene, central part, high concentration of sodium, room is low concentration of sodium. But in these rocks, we can see some globules. The composition of these globules is dolomitic with phlogopite and pyroxene. And we decided that it is the first stage of silica carbonate liquefaction. Minette dikes, we have phenocrysts phlogopite and pyroxene, no olivine and no phenocryst of feldspar. Because if we have feldspar and phenocryst, we have not possibility name these rocks as minette. Therefore, minette is lamprophile rock, and lamprophile rocks do not have phenocryst of plagioclase or feldspar. But in these rocks, we have little globules central part is carbonate. This is feldspar and some rooms of phlogopite, and composition of this phlogopite is differ. This part the same to phlogopite from grand mass of Minetta, but another crystals in these globules have low titanium composition than phlogopite in rocks. And these globules in composition are the same to large part of these globules in minute days. Here we have fluoride, we have feldspar too, and calcite too. And moreover, that in phlogopite phenocrysts we can see dolomite, calcite, barytocelestine inclusions, which show us that we have silicate carbonate liquefaction. And concentration of rare earth elements, barium and strontium, go to this carbonate phase, but not in silicate. Moreover, where we have phenocrysts of apatite, we can see the central part of this phenocryst have a high strontium concentration, but in room we have low concentration of strontium. Therefore, we can possibility to understand on what stage the liquefaction begin. In central part, liquefaction is not in room after liquefaction. In olivine lamproid, we have right zoning on phlogopite, low barium in central part and high barium in room of this phenocrysts. But when we can see another example, in Minette, we have high barium concentration in central part, but low concentration on barium in the periphery zone of this phenocrysts. But in cyanide, we have phenocrysts of phlogopite with right zoning again. And in cyanide, we can see only calcite in interstitial part of between crystals of feldspar, and this calcite without barytocelestine, only fresh calcite crystals. Therefore, we tried to show evolution of lamproid parent melt, and we decided this parent melt was high magnesium, and precipitate of olivine and chromite may be formed dunite massive in deep chamber as inagli massive. The late stage differentiation was by CPS and phlogopite, and on this stage we can see a first stage of carbon liquefaction, because it is dolomite phlogopite CPS globulus in these rocks. Then only phlogopite in phenocrysts differentiation in Mineta, and we can see carbonate with feldspar and a high concentration of fluoride, barytocelestine, and rare earth elements in this globulus. And in cyanide, we have only carbonate without rare earth elements. Therefore, we decided that deposits with rare earth elements and fluoride not be connected with cyanide, but they connected with this stage of evolution lamproitic magmas. Because only on this stage we have high concentration of barium, strontium, and rare earth elements in carbonate melts. Oh, I'm finished.
Thank you. Other questions? Pavel?
Repeat. Сейчас. 0.3, 0.4. Where we have high concentration of barium.
Other questions? Okay, thank you. That's it. Пожалуйста, следующий доклад. Это доклад Латышева. Представьте Латышева. Okay, I will show you 3 minutes.
My name is Anton Latyshev. My talk is about paleomagnetism of the Siberian traps and implications for the intrusive magmatic activity in large igneous provinces. So I present the scientific group from the Institute of the Physics of the Earth and Moscow State University. We have worked on Siberian traps paleomagnetism for several years. Here you can see the areas of our investigations. So we studied the most complete volcanic sections from the northern boundary of Siberian platform. It's Norilsk region and Maymechikotu region. And now I present results from 2 intrusive complexes from 2 regions. The first region is central part of Tunguska syncline. It's the Nizhnya Tunguska River Valley. And the second one is Chuna River. It's here. It's Angara-Taseeva Depression. So now the scientific interest in large igneous provinces is caused by several reasons. First of all, there are many problems connected with models of the LIPS LIP's formation, for example, the plume hypothesis and other questions of global geodynamics. Secondly, it's idea about the causal connection of mass extinctions and volcanic hazards. And finally, there are many problems of genesis of mineral deposits localized in traps. And solving all these problems, we must obtain detailed and reliable data about the time and duration of magmatic activity and the correlation between intrusions and volcanic sections. And we used the paleomagnetic methods solving these problems. So the main goals of this investigation are looking for the major magmatic events, estimation of the duration of total magmatic activity and discrete pulses, correlation of lava sequences and intrusions from different regions, and comparison of the styles of magmatic activity in the central part of Tunguska Depression and its periphery. We had obtained some results before. First of all, it was shown that formation of lava sections of Norilsk and Maymechakotn took place as a limited number of volcanic pulses and more prolonged periods of quiescence. Similar short and powerful magmatic events were distinguished in Angara-Taseva Depression and the east of Tunguska syncline. And based on the comparison of paleomagnetic direction, we suppose that ore-bearing Norilsk type intrusions are coeval with the Morangovsky-Makulaevsky level of Norilsk volcanic section. So this is the sketch geological map of the first region. It's central part of Tunguska syncline. This is the Nizhnya Tunguska River. Paleomagnetic sites are shown by as yellow circles, and this distance is maybe about 1,000 kilometers. Here you can see the typical outcrops of intrusions in the Nizhnya Tunguska River Valley. The majority of sampled intrusions are united to the so-called Katinsky complex. There are dolerite seals and dikes, and there is a separate group of so-called differentiated intrusions cutting all lava section. They are considered to be Middle Triassic according to the state geological map, but there are no reliable isotopic data. All paleomagnetic samples were undergone to the stepwise thermal demagnetization according to the standard procedure. And here you can see the results of thermal demagnetization. The quality of paleomagnetic record is usually rather high. Both normal and reversal polarities can be found. And here you can see the distribution of the mean directions per site for normal polarity and reversal polarity. Here are two important things. First of all, it's that reversal test is positive, so the mean direction for the normal polarity and reversal polarity are antipodal. It's an argument in favor of the primary nature of magnetization and argument that secular variations of geomagnetic field are averaged. So it was more or less a prolonged magmatic event. And the second, I think, is moderate values of K parameter is condensation parameter. It's rather high, but, for example, less than in a marginal part of Tunguska syncline. We calculated the mean pole for all sampled intrusions of the Nizhny Tungusk River. Here it is, and we compare it with the paleomagnetic trap pole, which was calculated for the Permian-Triassic boundary by Pavlov on the lava sections of Norilsk and Maymech-Chukotay. So you can see that these poles are very close, and it's another argument that secular variations of geomagnetic field are averaged. Here you also can see the mean pole for these above mentioned youngest intrusions, which cut all lava sequence, and it's clearly different from each other of these two poles, maybe because of the really younger age, maybe because of the briefness of magmatic event. So the conclusions for the Nizhny Tunguska River intrusions are, first of all, that both normal and reversal polarities, positive reversal test, and proximity of the mean pole for intrusions to the paleomagnetic pole indicate that magmatic activity was more or less even and prolonged in this region. If we correlate sampled intrusions with the volcanic sections, according to the paleomagnetic dated structural relationship, we can suggest that majority of sampled normally magnetized intrusions are likely coeval to the basalts of Kachichumsky formation in subpart of volcanic section of Tunguska depression. And the reversely magnetized intrusions cutting all the lava pile are younger than the main part of volcanic section.
3 minutes left.
Here is the second region, it's Angara-Taseva depression. The intrusions are represented by the large seals. Here you can see paleomagnetic sites. So here are the typical outcrops. The same procedure was performed, and as a result, all sites are magnetized in reversal polarity. So here you can see the distribution of mean directions per sites, and unlike the first region, the first case, here we can see two very tight directional groups. The first one here about 7 or 8, I don't remember, points, and here about 12. These tight directional clusters correspond to the two magmatic events expressed in intruding two large seals. And the remaining sites have intermediate directions. So we compare the mean poles for the Chuna River intrusions with the Angara River intrusions, and we can say, based on their proximity, that there were two very large magmatic events which took place simultaneously in Angara and Chuna regions. Here is the poles for the Podunsky seal, and here for the Tulunsky seal. And here are the comparison of mean poles with the paleomagnetic pole. As you can see, this for Podunsky seal, it's close, but we suggest that it's coincidence. And here we can see that pole for Tulunsky seal is clearly different from it. So the main conclusions are that the character of magmatic activity is really different compared with the central part. Here are several extremely tight clusters of paleomagnetic directions which correspond with the discrete short magmatic events. And these magmatic events took place the distance about 200 or 300 kilometers. And previous paleomagnetic data from other regions, our data and of our colleagues allows us to suggest that such pulsating character of intrusive magmatism is typical for the periphery of Tunguska syncline. I have no time, yeah? So that's all.
Thank you. Two short questions. Nick.
You mean exactly the time of reversal of polarity? There are many estimations about this. Most of them suggest that it's about first 1,000 years, 1, 2, up to 10. Yeah.
Time spans between 2 points of normal polarity. Can you just say something about this?
So you mean your question is which is how often the reversal took place in this system? For lower Triassic, it's about maybe first 100,000 years. The longest period in the lower Triassic is about 600,000 years.
Last short question, please. Nadежда.
Daldekan?
Could you please repeat the question?
Yes, I understand. So, the Daldekan intrusive complex is younger than all lava section of Norilsk and of maybe all Tunguska syncline. And I think that so does at least one of groups in Angara-Taseev depression. Podunsky seal is of reversal polarity 2, and we suggest that its emplacement took place just after the termination of the main phase. Maybe about the same. About the Tulunsky seal, I can't exactly tell anything because there are only argon-argon data which gives us a middle Triassic age.
Okay, thank you very much.
Thank you.
Следующий доклад, поставьте, пожалуйста, это Воскресенский. The next talk is by Воскресенский Anton, Structure of the
Chechelek, seismogenic fault,
Chechelek.
North Mongolia.
Yes. Chechelek strike slip fault is southwest, northeast, striking rupture in North Mongolia. Follows along northeast mountainside Shavarn Ridge and in Aigonur Lake Zone joins to Balnay Fault. We have divided the analyzed fault into 4 segments. I'm going to report about the first 3 segments. Okay. Fault is known that in its area there was Chechelek earthquake occurred 9 July 1905 with a magnitude of a I.S.E.S shock of Balnay earthquake occurred in 23 July with a magnitude of 8.4. The latest is the strongest of the known historical earthquakes. The fault zone with a northern east 65 degrees strike, length about 130 kilometers, are presented by opening fractures and compression faults. According to our field observations on the right bank of the Sengol River, near the epicenter of Chechelek earthquake, the amplitude of the left lateral strike slip is about 3 meters, at vertical displacement up to 1.5 meters. The study was designed to interpret satellite images available on resource Google Earth in order to allocate the seismogenic ruptures associated with the activations of movements along the Chechelek strike slip. The second goal of our work to compare the obtained regularities of orientation fractures in the zone of Chechelek fault in relief in the deformation zone with the published results of physical modeling on equivalent materials. Creation of database were made using the ArcGIS. Calculations were done by using OpenOffice Calc. Our data are interpreted of the basis of classification fractures and faults produced in the left lateral strike slip zone by Jean Pierre-Brook. Radial shears are the first shears to occur and build the most prominent set. They develop on acute angle, typically 10-20 degrees to the main fault. R-prime shears. The second shears to occur. They are oriented at a high angle approximately to the main fault. They may develop with or after R-shears, P-shears or compression faults. Faults symmetrically are oriented to R-shears with respect to fault. They are less common as R and R-prime shears and may require more displacement to form. Y-shears are faults subparallel to the main fault. Y-shears may all connect one another to form a network of fractures in narrow fault zone, which form a main fault displacement. This figure shows a process of development sinistral strike slip in 3 sequential stages. During the first stage, R and R prime shares occurred. The second stage is characterized by P shares occurred, and third stage is characterized by Y shares, and finally, single major displacement rupture is formed. Stress tensor. The reconstruction of stress field by using microfaults data shows that the fault displacement forming under strike slip regime of deformation with submeridional compression. As regards the modeling, Nasima Amatoy studied clay slabs. In experiments, the thickness of the clay slabs was varied, while the shear strength remained unchanged. These results are displayed visually in this figure. On the illustration is plain view of strike slip deformation zones in various models. Figure shows how radial shears are distributed in space. The shear fractures form a simple and echelon arrangement in model NA9, 2 centimeters thick of the model. A mixed form of an echelon arrangement with the domains of double to triple parallel traces in model NA4, 4 centimeters thick of the model. And more complex arrangement in model NA8, 8 centimeters thick of the model. So the height of the strike slip deformation zone is proportional to the thickness of the clay slab. According to our field observations, the minimum height of the fault zone is observed in areas of distribution of slope sediments which are characterized by low thickness of sediments. Increase of the fault zone height in the stream valleys is observed. It is an example of how we have measured the height of the fault zone and height of the valley. As seen from the chart, there is a direct relationship between these parameters. It shows the dependency of the height of the fault deformation zone of the thickness of sediments. So the thickness of the deformation layer controls the height of the deformation zone. Nowadays, the depths of opening fractures reached up to 1.5 meters, and height of opening fractures up to 2.5 meters. The length reaches tens and few hundred meters. The height of the compression faults reached up to 1.5 meters. Especially well open fractures remained on forested slopes of Tesingol River Valley. As seen from the photo, the height of opening fractures reached up to 2.5 meters and depth up to 1.5 meters. As in the models and that in nature analog, the process of forming the positive relief on the fault zone associated with the dilatation of sediments is well manifested. On eastern segment of the fault zone is narrow, likely as a result of the fact that the thickness of sediments in this area is small. According to the diagram, open fractures is very distributed. Also, we can allocate the submeridional R prime shares and R shares. On the right side of the Tesingol River Valley, near the earthquake epicenter, the amplitude of the left lateral displacement is about 2-3 meters, and the vertical amplitude reached up to 1.5 meters. In the junction zone, we can mark the increasing of the height of deformation zone. Main fault intersects with the submeridional one, which was also activated during the Tsetserlek earthquake. That's why the diagram has north and west high. The rest of the structure is previous one. Wide zone is associated with an areas of the valley where thickness of sediments is increased. The dotted red line shows the position of the main fault. In the valleys, there are fractures not associated with the movement along the seismogenic rupture. These fractures have formed as a result of motions flooded sediments downhill. When you shake the flooded sediments on low angle, plots are displaced down the slope. In this case, we have two such generation of fractures. One of them are developed in the bottom of valley and presented by open fractures filled with water. The earlier generation of fractures are observed in drained areas of the valley. Apparently, it occurred during an earthquake preceded Tsetserlek earthquake. This photo shows these opening fractures filled with water. And conclusions. Our data are found to be in general agreement with published results of on the structures of left lateral strike slip in elastic plastic and brittle materials, as in the models, and that in the nature analog, the process of forming the positive relief on the fault zone is associated with the dilatation of sediments is well manifested. In both cases, the direct relationship between the height of the deformation zone and the thickness of the model layer and the thickness of the unconsolidated sediments in nature is revealed. General irregularities of the formation, riddle shares, open fractures, and compression faults are well revealed in natural object and models. In bedrock fault, most often represented by a main fault, less frequently a series of subparallel fractures.
Only one short question. There is one, please.
Okay, we have selected, we have the widened fault into 4 segments. That's why, because we don't have the full paths of satellite images, we have only two parts of the fault, east and west, and because this lack of information, we have divided that way.
Thank you. Просто доклад Крашенинникова. The next talk is by Krasheninnikov Stepan, the test of liquid thermometry modeling, results of high temperature 1 atmosphere experiments. Go ahead.
So thank you and good afternoon, everybody. My talk is the test of volume liquid thermometry modeling and the results of high temperature 1 atmosphere experiments in gas mixing technique. So the understanding of the precise temperature values are a key question for modern petrology, and here you can see some examples of the previous studies based on this theme, and all of them have some restrictions, some pros and contras, and that's why we have mounted a brand new high temperature vertical tube furnace in Vernadsky Institute. So here are some technical specifications. You can see on this scheme that we have vertical ceramic tube surrounded by 4 heating elements which allow us to get a 30 centimeter heating zone, gas input from downside and gas output, and we put our samples inside the hot zone by putting them from the top. Some specifications of the redox control. We use a set of regulators and flow meters by Bronkhorst, which allow us to use a gas mixture of CO2 and hydrogen, and it allows us to assess this range of oxygen fugacity values around nickel-nickel buffer plus minus 3 log units, and temperature control provided by thermocouples type S and type B. We have a system of online record of temperature data to personal computer, and the stability of temperature regime during one experimental run lies within ±1 degree C. And the furnace temperature profile, as you can see on this plot, at different temperature values shows ±7 centimeter hotspot zone, with the temperature gradient less than 1 degree C. And a couple of words about experimental techniques which we can use on this furnace. The first one is the melt inclusions homogenization procedure, which Alexander already mentioned in his talk. And here some individual grains of olivine crystals were placed in platinum capsule and heated at needed temperature and redox conditions for 5 minutes, and then quenched from the bottom of our furnace. And here are some examples: unheated inclusions with spinel crystal glass, CPX, and here are already experimentally quenched inclusions in the microscope and backscattered electron image. This image is from the paper by Sobolev in Nature. So, and the main technique is the, okay. Okay, and the main technique is the loop technique procedure. We choose this technique because it allows us to obtain several compositions during one experimental run with the highest sample container ratio. We use fine powder of each sample, which was mounted on approximately 2 millimeter platinum loop with an organic glue and placed on the ceramic stick holder. As you can see on this image, it's a stick holder, and here are our already quenched samples. We've made approximately 20 experiments with the natural mafic and ultramafic compositions at high temperature from 1300 to 1600 degrees C, and a range of nickel-nickel plus minus 2 log units buffer condition. Each experimental run contains from 5 to 6 loops with different composition, and the major elements in these glasses, olivines and spinels, after experiment were measured by microprobe and Grenoble using precise olivine protocol. Here are our sample data set. The red circles are the whole rock compositions, yellow triangles are our glass compositions. So the blue area is the comatites, whole rock from the literature, and purple and black dots are previous studies, experimental data on glass compositions. So Alexander already told that we have provided experiments on the compositions with more magnesium, titanium, and some different characteristics. So there is, experimental results. I want to start with these two plots, where you can see Forsterite number versus nickel and calcium. And you can see black dot is average or mean value, and the gray one is the individual analysis. So highly homogeneous olivine composition could be used as an equilibrium criteria, and standard deviation of Forsterite values is on average of 0.01%, and doesn't exceed 0.07. So, for example, for these samples, you can see only black dots, only average composition. So the point is bigger than the range of individual compositions. So, and another kind of equilibrium criteria is the model by Topliss, where we use partition coefficient measured versus partition coefficient of ferromagnesium calculated. So in this model, if the value is in this range of plus minus 10% of partition coefficient, then we can say that the equilibrium had been reached. So ferromagnesium partition coefficient values for 71 experimental run shows that the equilibrium conditions had been reached for our experiments. And on this backscattered electron image, you can see the distribution of olivine crystals, the dark one, and white are spinel crystals. So and gray mass is glass quenched during the experiment. And we tried to analyze thermometer models that we have. And in paper of Loon, it was shown that the best suitable models for our compositions and our temperatures is a model of Ford and the model of Herzberg and O'Hara. So we tried to compare our temperature, which we had measured directly during the experiment. On this plot is here, and also x-axis, and different models temperature calculated. So the black dots are for Ford model. We can see it quite nice, but with some error, plus minus 40 degrees C. And the model of Herzberg and O'Hara, gray dots, which has much more range in values. So we try to compare, and here you can see the temperature of the experiment versus delta T of experiment minus the calculated. For Ford model is black, and for Herzberg. So you can see that in the range of lower temperatures, less than 1400 degrees C, they are quite similar, these two models, but on the hotter conditions, they shows different results. So used models form uniform trend of calculated temperature at low temperature and growing difference with the experimental temperature ascent. And in situ temperatures, which shows with this black line, measured with the thermocouple at the higher temperatures, generate somehow values between chosen models. Okay, thanks. Okay. And we've made experiments with different redox conditions, and on this plot you can see our temperature versus difference between two models, Ford and Herzberg, and the different symbols are for different redox conditions. So these gray triangles are for delta nickel 0 these blacks black ones is for 0 delta nickel core, and it's more oxidized and more reduced conditions. So the difference between these two models increased not only with the temperature of experiment, but also with the ascent of oxygen fugacity values. And the maximum was about 100 degrees C between these two models. And the summary is, for that study, the brand new high temperature Nebertherm vertical tube 1 atmosphere furnace mounted and launched in the Vernadsky Institute. 20 experiments conducted using the loop technique at the range of 1300 to 1600 degrees C, and nickel-nickel plus minus 2 units buffer conditions. Compared calculated temperature values show significant difference at higher experimental temperatures and redox conditions. And we suggest that the reported data shows that new updated quantitative model of olefin liquid equilibria should be developed for high temperature ultramafic melts, and that such a study could be done in the base of presented furnace at Vernadsky Institute. Thank you for your attention, and here is the spin effects structure from one of our experiments.
Thank you. Time for a few questions. Go ahead.
Do you control oxygen fugacity inside of your furnace by zirconium cell?
Actually, it's a good question because we try to get this zirconium because we have quite big, we need quite long zirconium, but we couldn't order it yet. So it's a questionary, but we try to calibrate our flow meters and
John?
You showed that your KDs were always a bit higher than topless.
Yes. Yeah.
Why do you think that is?
In this model of topless, he mentioned that it could be two ways. If all of the KDs are higher and lower, and one is because of the longer time of the experiment, the water can affect somehow on the KD, and also because of the ferrum 2 plus and 2 and 3 plus ratio, it also can provide some effect.
He makes no correction for ferric iron.
No.
Did you measure the ferric iron?
Not yet, but we want to make it. Yeah.
We have calculated these iron 2, iron 3 ratios using our conventional models.
Yeah.
Using our oxyfugacity control. Normally we use Borisov-Shapkin model, which is especially done for ultramafic magmas.
Yeah, this correction was made in Petrolog software. So.
Vadim? Please show your slide.
Okay. As I shown, I tried. yeah, tricky system.
Looks like
yeah,
distance.
this one.
Yeah.
As you can see, the individual analysis show the quite small variation in the composition, not only in the first red number, but also in calcium, nickel. And we measured pores of the grains and also the rims. So actually almost no zonation, no difference in these two parts of grains usually. But we have some samples with which were almost fully crystallized during the experiment, and this runs is not so good for to use in these calculations. So we try to avoid them.
Okay, I think we have to stop and to shift to have a very short coffee break. And
thank you very much.
Please be back quite soon. We're waiting you not more than 10 minutes. Следующий, Назарова. Она пока потренируется.
Я думаю, что я разберусь.
Нет, давай ты потренируйся, у тебя есть время сейчас.
Не, ну нормально. А, ну вот сюда его направлять или туда? Туда? Все нормально. А обратно что-то не листается. Все, я могу начинать? Да что ж такое-то? Не хочет оно обратно. Нет. Нет. Вот, пусть будет все. Я не буду переживать.
работает.
Well, let's begin, please. The first talk is Daria Nazarova. 15 minutes, please.
Okay. Hello. I want to present results of the study partial water loss from melt inclusions in olivine and its initial content in Karymsky volcanomagmas. It's Kamchatka. Water plays an important role in formation and evolution of arc magmas. In this work, we estimated initial water content in primitive magmas of Karymsky volcano. Karymsky volcano located at the front of central segment of eastern volcanic belt in Kamchatka. The sample which we investigate is a volcanic bomb from the northeastern side of Karymsky Lake, from base of the lower terrace. This composition of studied rock, this rock is one of the most primitive to Karymsky volcano. We investigate two types of melt inclusions in olivine from this volcanic bomb. The first type are natural glassy melt inclusions, which consist volcanic glass and gas bubble. And the second type are partially recrystallized melt inclusion and partially recrystallized melt inclusions were homogenized experimentally to eliminate effects of partial crystallization. Experiments were carried out at a vertical furnace at Vernadsky Institute. The heating was performed in the atmosphere of carbon dioxide and hydrogen gases mixture in proportion corresponding to nickel-nickel oxygen buffer. Loose olivine grains with melt inclusions picked under microscope were loaded in platinum capsule and heating during 5 minutes at 1300 degrees and then quenched in water. After the experimental treatment, melt inclusions containing glass, gas bubble, and spinel crystal sometimes. Major elements in glasses, olivine, and spinel were analyzed by electron microprobe at GeoMar. All inclusions were corrected for equilibrium with host olivine with ferrum loss using Petrolog software and initial iron oxygen in the inclusions was assumed to equal iron oxygen in their host rock. Water content? Water content in glasses of melt inclusions, natural melt inclusions and heated melt inclusions were determined by confocal Raman spectroscopy at the Moscow State University. And the measured water content in glasses of melt inclusions is 3.2 for 4.4 weight% for natural glass inclusions, and 2.3, 2.4 weight% for heating inclusions. And between the water content and inclusion size, possible observe positive correlation. This correlation can originate due to partial water loss from melt inclusions at nature and maybe at experimental heating. And this correlation may due to that small inclusions will lose faster, maybe. And in order to understand the measured water content corresponds to the original water content in parental magmas or not, we estimate water content by model described in article Sobolev and others, and our article. This method based on comparison of real crystallization temperature and dry crystallization temperature of olivine. Dry crystallization temperature is equilibrium temperature of olivine dry melt, and real crystallization temperature it's equilibrium temperature of olivine spinel. This picture from our article in press. Dry crystallization temperature. Dry crystallization temperature were calculated using the composition of melt inclusions in olivine by model Ford and other, and temperature for forsterit 87, its average, is about 1220 degrees. And real crystallization temperature were obtained using the composition of melt using geothermometer aluminium in olivine. It's article Kugan. It's geothermometer based on aluminium portioning between olivine and spinel. This temperature was found to be about 1114, and this temperature were calculated for 19 parts of olivine and spinel. In this picture, shown difference of dry crystallization temperature and real crystallization temperature. This difference is about 111 degrees. And if we know difference temperature delta T, we can estimate water content. To evaluate the original water content, we used a model, Almeyev. It's based on the significant influence of water presence in the amount of olivine liquidus temperature. And we know delta temperature, what corresponds water content about 4.2 weight percent. We compared this data, we compared the measured water content and calculation of water content in picture. Shaded area calculation water content in melt inclusions, green symbols and red symbols is measured water content by Raman spectroscopy at this work, and black symbols it's published data, Portnyagin and others. It's measure water content by I.S.E.S. Calculate and measure water content. It's in its largest inclusions. They're similar within the air, and so maximum value of measured water content corresponds to minimum calculation water content. And we think that the calculation estimate of water content more accurately. And we think that natural glassy inclusions lost no more than 1% of initial water content. At this slide, shown picture from article Planck, water concentration in melt inclusions from 7 volcanic arcs in average 4 weight percent, and estimate water content calculation, estimate water content of the parental magma Karymsky volcano. It's red symbol. We think that's similar data. And conclusions, initial water content of the parental magmas of Karymsky volcano, it's about 4.2 weight percent. Calculated and measured initial water content in the largest inclusions are similar within the air, and maximum value of measure water content corresponds to minimum water content at the source. Even large inclusions can lose water. Inclusions can lose up to 1% initial water. And we suppose that calculated method for estimating water content can be used for other subduction zones. Thank you.
Thank you. Please, your questions. Please.
How much of the missing water do you think is in the gas bubble? Do you think the gas bubble is all carbon dioxide?
This is small.
How do you know? Have you analyzed the gas bubble?
Как мы не оценим? Нет, we don't analyze the gas bubble, and I don't think about it. But thank you.
It's quite important, unless the melt inclusion tracks the gas bubble when through. The gas exsols to form the bubble after the inclusion is tracked. So some volatiles, mostly carbon dioxide, remain
Оп. О.
So it's a discussion, I think. One more short question.
Я не слышу. Я не слышу, вообще не слышу. Окей. И... Ну... Оно вперед идет. А там можно как-нибудь переключить, нет? Назад. Там, где график с зелеными и красными точками. Вот, да. Mm-hmm. In last slide, measured water content, and this recalculated to for street 90. Because we calculate for...
Thank you. The next talk is Viktor Upatenko. Please, 15 minutes.
Hello, everybody. I'm sorry, but my topic will be very difficult from previous ones. I want to talk about GPS and GLONASS observations and how it can be used in modern geodynamics, seismology, and tsunami early warning systems. Okay. The first global navigation satellite systems, GPS and GLONASS, were designed as a meter-level precision positioning tools for military purposes. But now they allow users to estimate 100 times more precise coordinates. Here you can see an example of satellite constellations and two typical site installations. There are two main methods of GNSS data processing. In static mode, we calculate daily average coordinates. The precision is up to 1 millimeter. In kinematic processing mode, we calculate instantaneous coordinates. The precision is up to is about 1 centimeter. We usually calculate coordinates every 1 second. Let's look at some details of the static coordinate time series. Here you can see 18 years daily average coordinates of one of the stations in Japan. There are two sleeps, and second one is seismic sleep caused by 2011 Tohoku Oki earthquake. There are also 3 long-term slow sleep events, which are slow earthquakes that last for several months. You can also notice some velocity changes of the station. For example, here, before and after Tohoku Oki earthquake. The strong earthquakes lead to seismic sleeps, permanent positioning changes of the surface which can be measured by GNSS stations. Using seismic sleeps determined as the number of GNSS stations, one can determine size and orientation of the earthquake source, sleep distribution in it, and seismic moment and moment magnitude. To date, it becomes a relatively routine processing strategy for strong shallow earthquakes. But here you can see source modeling results for the 2013 Okhotsk deep focus earthquake. Seismic sleep can also be determined using kinematic processing results. Here you can see the comparison between static and kinematic solutions. You can see that a kinematic solution is much worse than static one, but it can be determined faster, even in real time. How it's possible to process GNSS data in real time? In the table, you can see 4 product types of satellite clock corrections and orbits, and corresponding satellite antenna distance errors. While predicted orbits are precise enough, both real-time clocks lead to enormous distance errors. So if we need to use satellite clock corrections, we must use low latency data streams such as I.S.E.S CLK01. How these corrections are made? In the map you can see I.S.E.S real-time station network. It covers almost all the world except Russia, where only one station available. Real-time GNSS data from more than 170 stations collected at data service, from which users and more than 10 analysis centers can get it in real time using a special network protocol. Analysis centers calculate clock corrections, which becomes also available for users in a few seconds. The earthquake early warning system using seismic and the GNSS data is being now tested in California. It's shown that earthquakes with magnitude 6 or more can be successfully registered and processed within several tenths of seconds using real-time data obtained from GNSS stations. There are 2 main problems of tsunami early warning systems, and both can be solved using real-time GNSS data. The first problem is rapid estimation of the strongest earthquake's magnitudes. Seismic data do not allow estimating magnitudes of the strongest earthquakes within tenths of minutes. In the diagram you can see the comparison between seismic derived and GPS-derived magnitude of the Tohoku Oki earthquakes, which have magnitude 9.0. Magnitude underestimation leads to the tsunami hazard disparaging. The second problem is false tsunami alarms. For the coastal regions close to the epicenter, the only method for tsunami hazard estimation is magnitude criterion. This leads to inadequate amount of false alarms. For example, in 1994-2010, only 11% of the warnings produced by Russian Far East Tsunami Warning Service were true. The earthquake source model based on GNSS data can be used for determining tsunami probability and even as the initial data for tsunami modeling. There are only few requirements. Seismic slip at a number of relatively well-distributed stations must be determined reliably and fast. In this work, we have developed a new method for increasing the seismic slip estimation accuracy. The method based on simultaneous GNSS data processing using two approaches. The first one is precise point positioning, or PPP. It gives absolute antenna coordinates, but requires satellite clock corrections. The second one is relative positioning. It gives coordinates of the rover relative to some base station. In other words, differences between coordinates of two stations. Both methods allow achieving high accuracy level. Next slide, please. Consider that we have n stations. In suggested method, we calculate a weighted average of the n calculations of seismic slip for every station. We have tested the suggested method on 2 data sets of 6 stations, and more than 18,000 test slip errors have been calculated for statistical analysis. The result obtained in delay is about 5 minutes, and the suggested method can be used with real data without significant changes. Here you can see some results for the first data set. In the left diagram, you can see statistical distribution of plane slip errors. Blue is PPP only, and black is with suggested method. In the right diagram, you can see relative slip error reduction. If we need reliably determination of seismic slip, we use 95% probability. For this probability, mean slip error reduction is 41%. The same results, but for second data set. Please note almost twice lower initial PPP errors. It leads to less error reduction, only 15%. So conclusions. GNSS is not only things in our mobile phones. It becomes a strong geodetic method for studying different types of geophysical phenomena. Now it's widely used in geodynamics and seismology. Earthquake source modeling based on GNSS derived seismic slip can be a part of earthquake early warning systems and can help to solve 2 main problems of tsunami early warning systems. In this work, we developed a new method for increasing the seismic slip estimation accuracy. The suggested method decreases mainly gross errors. Slip errors reductions with 95% probability vary from 15 to 41% for 2 different data sets. Thank you for your attention.
Thank you. Your questions, please. No questions. Please, Richard.
What are the possibilities then of extending that network into Russia?
I showed I.S.E.S real-time network. It's in Russia there are many stations, but they are not in real time. They do not allow our rules in our country do not allow to give some data for everyone, especially for foreign users.
Please.
As I understood, you try to discriminate normal fault and
No.
strike slip
Yes, yes.
It's just judged from statistics of your registration. So it's pure mathematical approach.
Yes, yes. It's only first step in this.
So it's not something which really bring you a new level of discrimination of this what happens actually.
No. It's very simple model. Only 1 or 3, 5 planes with often stable sleep, without dynamics, only static.
Thank you. We have time for one more short question. Well, thank you. And the last talk in this session, Anna Dolgaya.
Hello, dear colleagues. Thank you for your patience. My report is about the results obtained by our scientific group in recent years during the research of temporal, spatiotemporal, and energy patterns of planetary seismic and volcanic process. The analysis of the works on the theme of research has shown that regional approach, which is very often nowadays, doesn't allow to see the whole picture. So it's reasonable to use the planetary approach, and we need so as possible as it can be complete lists of events in wide energy ranges. Also, we conduct our research under the concept of block structure of geomedium and under the concept of wave nature of geodynamic activity and process. So for the research, we compiled lists of earthquakes and volcanic eruptions around the world and sorted these lists by the date. And for processing and storage convenience, this information was presented in the form of a database, which statistical parameters are shown in the table. Each event in our database is characterized with a date, coordinates, and energy characteristics, which is magnitude for earthquakes and volcanic explosivity index, V, for volcanic eruptions. V corresponds to the erupted volume of erupted material. So we investigated different regularities of this data. First of all, we research temporal regularities and used two methods, spectral free analysis and spectral correlation analysis of time series, and this is the result of investigation of periodicity or cyclicity of seismic activity. This diagram is built-in axis of periods in years and the part of periods in the whole spectral lists of periods we identified with these methods. The same research was conducted for volcanic eruption time series. Next slide. Thank you. So we analyzed all these periods, and this is a summarized diagram which present blue dots for seismic periods and red dots for volcanic periods, and we found that there are the same periods for both processes, and the main period is about 250 years, and even periods of 500, 1000, and 2000 years. The value of the main period was confirmed by independent method that indicates its reliability. Parity of periods refers to the fact that all active zones of the planet together form the closed system. And the existence of periods common for both these processes, seismic and volcanic activity, allows us to consider these two processes as part of one uniform geodynamic process. This geodynamic process is within the tectonically active regions of the Earth appears in the form of earthquakes and volcanic eruptions distributed along the narrow and long belts. In detail, we studied three of such tectonically active regions. It's Pacific Ocean margin, Alpine Himalayan belt, and mid-Atlantic ridge. These three regions together have more than 90% of our seismic and volcanic events in our database. This picture shows with blue circles epicenters, earthquake foci of with magnitude 7 and more, and red triangles are erupted volcanoes, data of which eruptions we have in our lists. So such geographical distribution of these events allow us to consider the seismic and volcanic process as the sum of one-dimensional sequences of events taking place along the axial lines. They are presented as black lines along the belts. In mathematical theory, in the theory of stochastic process, this model corresponds to a one-dimensional random walk, which is generated by a sum of mutually independent and identically distributed variables. They are called Markov chains. To find the distance of the coordinate along these axial lines for every event, we use the equation which is presented in the slide. Using a special algorithm, let us make it possible for us to decompose the entire set of data into sequences of events. We call these sequences migration chains of earthquakes, foci, and volcanic eruptions. The algorithm is described on the slide, and using this algorithm and its program which optimized this research, we obtained a large number of migration chains, which are graphically demonstrated in the diagrams with axis time in years and distance along the axial lines in kilometers. As you can see, these migration chains in the graphs are rather good approximated with a linear function, which slope in these axes has the meaning of velocity. So each chain in our research is described with the duration, extent, energy range, and the velocity. This is just one of examples of migration chains for seismic activity, it's upper row, and volcanic activity, it's lower row for Pacific Ocean margin, for Alpine Himalayan belt, and for mid-Atlantic ridge. Here you can see energy ranges and estimates of velocity for each of this chain. This slide shows how the migration chain can look like on the map and on the graph. This is the example of one of migration chains of earthquake foci along the Pacific Ocean margin, and two examples of migration chains of volcanic eruptions in the same region. So I repeat that we obtained a lot of data about migration chains. Here's a table that shows so our data. It's an average estimations of parameters of earthquakes, migration chains, and volcanic migration chains. They're shown in this table. Yeah. And we analyzed this data and found very interesting and unexpected fact. The fact is that there are some dependencies between energy characteristics of migration chains and their velocity characteristics. And these characteristics, these dependencies, are graphically shown on this slide. This again, the upper row is seismic dependencies, lower row is volcanic dependencies for Pacific Ocean margin, Alpine Himalayan belt, and mid-Atlantic ridge. The axes are magnitude or way energy characteristic and a logarithm of migration velocity. We can see that these dependencies are also good approximated with linear function, and the mathematical estimation of the slope of these dependencies are presented here. It's a very interesting fact that for seismic dependencies for different regions, the slope has a different form. It is positive for Pacific Ocean margin and Alpine Himalayan belt, and it's negative for mid-Atlantic ridge. I should say the slope of these dependencies we call it the p-value. So the p-value is different, and how we can explain this? We thought about this fact and concluded that the explanation can be so. Alpine Himalayan belt and Pacific Ocean margin, as we know, are the regions of predominant subduction stresses and compression zones, and the mid-Atlantic ridge is a region of stretching. So we can see that our p-value is somehow sensitive to the tectonic setting or tectonic setting of the zones. It's positive for subduction and negative for stretching. How we can explain all negative p-values for volcanic eruptions? In our model, all volcanic belts we can regard as regions of prevailing stretching stresses caused by magma rising during the eruption. So we analyzed the slopes of our dependencies, and it has shown that the sum of values are close to zero, considering the accuracy of its estimation with approximately equal in absolute averages of positive and negative values. So the p-value is a persistent vector variable. There is a summary. I will not read it aloud. I just say that we are supposed to consider our p-value as an analog, geodynamical analog of angular momentum of geodynamic process. And our co-author Alexander Vikulin in his book proposed the rotational model of seismotectonic process on the example of Pacific Mountain, and the motion of blockchains in this model is described with the Sine-Gordon equation. This interact elastically. After interacting, they don't change their structure. And in the framework of our rotation model of geomedium, this property of geodynamic perturbations allow us to describe the migration of seismic and volcanic activity as a process with the property of long-range actions. So this solution, it's a solution of soliton in a physically understandable way depends on the modulus of momentum. We just should open the brackets and we can get modulus of momentum. So I have no time, and it's a conclusion of our work. Just as a result of our research, we constructed a mathematical model of migration process. We developed numerical methods, and it all together made it possible for us to get data for explanation of the available evidence of patterns of temporal, spatio-temporal, and energy distribution of seismic and volcanic process within the tectonically active regions of the Earth. So, thank you.
Thank you. Your questions, please. Please.
I try. Previous slide, the second slide, please show us. Сначала второй, который. It's about database, yeah?
No, it's about Gutenberg equation and parameters.
Yeah. Mm-hmm. Yes. It says it's okay, database.
Here you make a cutoff of the negative earthquakes, 6 or 5 or 9. And here on the left, on the right side, you make a cutoff of volcanic eruption volume 1. It's artificial. I can make it differently. Why you choose 1 for volcanic eruptions and why you choose 6 for earthquakes?
Oh, okay. The explanation is that we use data of very significant events, and we use data of long periods of time. And strong events can reform, maybe in some ways, its environment. And we can get information about only strong events of 1,000 years ago. So eruption too, and it's easy to get information about eruption and just with way 1. But I should say that our list is more complete for way 2 and more for eruption list. And there are a lot of catalogs of earthquakes with less magnitude, but we conduct our research on the basis of very strong events where each event is significant, just it without aftershocks or foreshocks. Because if you research, if you model earthquakes with less magnitude, it's very often it's a foreshock or aftershock of a more significant event. It's our position, just.
Next slide, please. Okay, here, for example, you compare two spectrums. Now, my question is, if I take a random distribution, would I get something very different from this spectrum, or it would be the same? With the same amount of statistics, you take here 100 earthquakes or 100 volcanic eruptions randomly, and you calculate the spectrum, would it be very different from this one?
I don't think that it will be very different because we observe very long range, long period of time, and if we have more complete lists for weaker events, I think it will be the same picture. The structure of this picture will be similar. It's 2,000 years. The last period we have 2,000 years. Of course, we have these peaks, but it's short-range actions between earthquakes. We don't speak about this part of periods. Just a tail, if I can name it.
Thank you. Richard, please, very short question, one more.
When you're talking about earthquake or earthquake migration or volcanic migration, are you looking at one volcano, next volcano, next volcano, next volcano on the chain? This is not my field, but I'm trying to understand the migration aspect. Is that you have an earthquake or a volcanic eruption here, and then somewhere along the chain you have another eruption, and the next?
Yes.
But presumably it's kind of here, then randomly here, then back here. Is there a sense of migration in one direction?
I understand your question, yes. This is just a model, a statistical, it's a model. And we just need to decompose the amount of events which maybe sometimes are linked between each other. We decompose it for random sequences of events. So we use the algorithm with according to which we use earthquake, and then search for another earthquake which is further along the belt and further and later in time. We have a direction.
You only search one direction?
Yes, but we use one direction. But if we change the point of the beginning of our direction, the picture doesn't change it. We saw it, we tried it, and our dependencies are the same. It's just a statistical model to decompose the amount of events. It isn't. It has not physical maybe base. It's mathematics.
Thank you.
Thank you.
And I think next point of our program is poster session now.